My name is Dave Eaton. I'm chairing this committee. I'm a professor of environmental and occupational health sciences at the University of Washington in Seattle. What we will do now as a first order of business is to go about the table and have people please introduce themselves with their name and their affiliation. And we'll start to my left. Jeff.
All right. Chad Blystone, NTP, NIEHS.
Dave Malarkey, NTP, NIEHS.
Michael Wyde, NTP, NIEHS.
Miles Capstick, ITIS Foundation.
Nils Kuster, ETH Zurich and ITIS Foundation.
John Ladbury, National Institute of Standards and Technology.
Wolfgang Kaufmann, retired director at Merck in Germany.
Susan Felter, Procter & Gamble.
I'm Rick Adler. I work for GlaxoSmithKline.
Mark Klein, Wake Forest School of Medicine.
George Corcoran, Wayne State University.
Lydia Andrews-Jones, Allergan.
Tyler Malice, Data Management Services. Larry Whiteley, Pfizer.
Matthias Winke, formerly Bayer, now retiree as well.
Kamala Pant, BioReliance, Millipore Sigma, Rockville, Maryland.
Jack Harkema, Michigan State University.
Frank Barnes, University of Colorado, retired.
Asimina Hurti, Ohio State University.
James Lynn University of Illinois, Chicago.
Mary Wolf, NIHS NTP and designated federal official.
John Bucher, NIHS NTP.
Galen Kepke, I'm retired NIST.
Ed Mantiply, FCC.
Gonçalo Gamboa, FDA Liaison Officer to the NTP.
Edmar Jerison, Food and Drug Administration.
Chris Bourne, Duke University.
Kaden Bird, ICF.
Jeannie Liu, ICF.
Virginia Guidry, NIEHS Office of Communications.
Louis Slesson, Microwave News.
Carl Blackman, Wake Forest University.
Gabrielle Wilson, EPL.
Tom Steinbach, EPL.
Don Stump, Charles River, also representing NTP Board of Scientific Counselors.
Russell Owen, U.S. Environmental Protection Agency.
Sheba Churchill, Charles River for NTP.
Donna Webb, NIEHS, NTP.
Andrea Bornoli, NIHS.
Amy Briggs, Contractor, NTP, NIEHS.
Christine Witt, NTP, NIEHS.
Mark Sesta, NTP, NIEHS.
Keith Shockley, NIEHS.
Kyatanahali Janardhan, Integrated Laboratory Systems.
Robert Sills, NTP, NIEHS.
Michelle Cora, NTP, NIEHS.
Susan Elmore, NTP, NIEHS.
Joe Elder, Consultant. My travel is supported by the MWF, the Mobile and Wireless Forum.
Ron Herbert, NTP, NIEHS.
Molly Balland, NTP, NIEHS.
Angela King Herbert, NTP.
Nigel Walker, NIHS NTP.
Michelle Huth, NTP, NIEHS.
Georgia Roberts, NIEHS NTP.
June Dunick, NTP, NIEHS.
Dory Gurmalik, NTP, NIEHS.
Matt Stout, NTP.
Vicki Sutherland, NTP, NIEHS.
Has everyone introduced themselves? Okay, thank you. I'm pleased to announce that Don Stump, who introduced himself over there, is the NTP Board of Scientific Counselor liaison to this meeting and will provide a brief report back to the Board of Scientific Counselors at their next meeting. Dr. Stump does not participate in the peer review. It's now my pleasure to turn this over to Dr. Bucher.
Well, thank you very much, David. I want to thank Dave, first of all, for agreeing to chair this meeting. I'd like to thank all the panel members for all the work that you've done in preparing for this meeting and coming today. And this is a culmination of a multi-year project, and we're all looking forward to a terrific couple of days to go through these findings. Just to give you a little bit of an orientation, the first day is going to be primarily going over the technical aspects of the radiofrequency radiation exposure facility. And we have a special panel of experts who can bring together the physics and biology to give us a good assessment of the chamber exposure facility, the dosimetry aspects, and the verification of those facilities and the radiofrequency radiation exposures. The second day is going to be starting into the biology of our exposure systems. The mouse studies, the rat studies will then follow on the third day. The panel is primarily, the second and third day panels are much larger than the first day panel, but the panel members are welcome to participate throughout all 3 days. What we hope to do is have a very thorough discussion of the issues that are brought up, and hopefully we can all come together and have a much better understanding of whichever way your background comes to this particular data set, and understanding the interrelationships of the physics and the biology that we're going to be dealing with. So just to give you a little bit of more formal introduction, the meeting over the next 3 days is similar in many respects to those that we regularly hold to engage experts to peer review the findings of the rodent toxicology and carcinogenesis studies that are carried out by the National Toxicology Program. But there are a number of ways in which the studies on radiofrequency radiation have differed from the others that we've done, and the audience differs for this review as well. So typically at these meetings we report findings from studies of chemical agents ranging from industrial chemicals, contaminants in food, water, or air, to selected drug therapies, all the way to dietary supplements. The studies are carefully designed to address specific questions for each of the agents, but there are commonalities to our approaches. Our usual peer review meeting presentations would not necessarily cover these common aspects, but because of the broad interest in the radiofrequency radiation studies, we decided to add presentations on our typical study designs, performance, data review, and analysis steps. The NTP radiofrequency radiation studies are the most expensive and technically challenging that we've ever undertaken. And because of this, we engaged with technical experts in all aspects of their design and execution. The complexity of these studies extends beyond the specially designed exposure system to include the interpretation of the findings and to the placement of these findings into a public health context. The studies are designed to identify potential health hazards and do not directly establish human risks. Establishing risk is a subsequent step, taking both potential hazard and exposure into account. In that respect, the kinds of studies we do to form the basis for understanding and calibrating potential human risks. Our studies explore potential biological effects of exposures that would appear to be extreme in relation to those we might encounter in everyday life, but this approach is the basis for essentially all health and safety information that the regulatory agencies rely upon to assess human health risks. These specific studies contribute to a large existing literature of human, experimental, animal, and mechanistic findings on radiofrequency radiation. and it's essential that they receive the rigorous peer review that we'll be carrying out over the next several days. Most of you are probably aware that we released partial findings from the studies in rats in the form of a pre-publication report in bioarchives in May of 2016. In an initial assessment of the findings from our study laboratory, IITRI ITRI in Chicago, our eye was drawn to two tumor types in the male rat studies: Schwann cell tumors in the heart and glial cell tumors of the brain. We carried out a complete review of the evidence for these tumors and indicated in that report that we thought that they were likely related to the radiofrequency radiation exposure, and that we had more confidence in the association for tumors in the heart than in the brain. The draft reports being reviewed over the course of the next several days include these findings, along with complete data from both rat and mouse studies. The complete tumor findings are interpreted in the context of the categories for strength of evidence that NTP uses for our cancer studies, and that Dr. Blystone will be reviewing later in the meeting. Because you'll be hearing presentations from a number of people, I thought I'd take a minute to introduce some key players in these studies. I mentioned these studies were a collaborative effort between the NTP staff and technical experts, and we drew heavily on the expertise of Drs. Perry Wilson and John Lairberry from the National Institute of Standards and Technology in Boulder, Colorado. And you'll hear from John later when he talks about their efforts to validate the radiofrequency radiation exposures that we achieved in the reverberation chambers. Dr. Niels Kuster and Miles Capstick from NIEHS in Zurich, Switzerland, provided invaluable contributions in the design and construction of the chambers. And in his talk today, Dr. Capstick will walk through the chamber performance specifications along with extensive dosimetry estimations. Dr. David McCormick and his team at ITRI in Chicago did a stellar job at carrying out these enormously complicated studies. And here at NTP, Drs. Ron Melnick and Michael Wyde were the primary study scientists for these studies. Ron was heavily involved in the design aspects of the studies, establishing the exposure facility in Chicago, and in the initial pilot exposures. Michael took over the study scientist duties from Ron when he retired. Ron will be giving public comments tomorrow from his private citizen perspective. Drs. Mark Sesta and Amy Bricks were the principal NTP pathologists. Dr. Chad Blystone coordinated the internal staff scientific reviews and oversaw the study interpretations. And finally, before we begin the review, I want to acknowledge many other staff who have put in many long hours in pulling these data together, preparing these reports, arranging the meeting, and all the other things that have to be done to make this meeting happen. And with that, again, I thank everyone for coming, for your attention, and for your discussions today and tomorrow and the next day. And with that, I'll introduce another key member of the team, Dr. Mary Wolf, who's serving as the designated federal official.
Thank you, John. Mary.
Good morning. I'll read the conflict of interest statement. Members of the NTP Technical Reports Peer Review Panel serve as independent scientists and not as a representative of any organization. Each member is to exercise judgment as to whether a potential conflict of interest might exist for the topic under discussion by the panel due to his or her occupational affiliation, professional activity, or financial interest. This potential for a conflict extends to the member's spouse, minor child, partner, or organization. Panel members are asked to bring to the attention of the federal official and the panel any potential conflict, and it will be handled in accordance with departmental policies and regulatory requirements. Each of you on the panel went through conflict of interest screening prior to our confirming your service, and you signed a pre-meeting certification form. I'm now going to pass around a meeting form and ask you to reaffirm the fact that your conflict status has not changed, please. So if you just sign and then pass it around. I have a couple announcements, please. As you all know, we have microphones at your desk. Please use them. You turn them on and off just by simply touching. When you make a comment, we ask that you please introduce yourself. People are watching on the webcast, and they'll make it easier to identify who is speaking. The caption video from the webcast will be posted to the NTP website a couple of weeks after the meeting. It takes a while to get the video ready. It has to be made compliant to federal rules for vision and hearing impaired accessibility. In addition, the NTP will be posting a small gallery of pictures from the meeting on the webpage if people want to use them. With regard to the meeting's proceedings, following the meeting, NTP will do two things. One, we will post a short summary of the meeting with the actions and recommendations from the panel. We hope to have that on the website by Thursday. In addition, we'll be preparing a meeting report that will be shared with each panelist so that you can review the report and ensure that we adequately captured your comments on the draft technical reports. You cannot add any new information to that report, but you can certainly, we want to be sure that we captured what you did say, what your statements were correctly. Also, the slides from the presentations of the next 3 days will also be posted to the NTP website once they are made 508 compliant for accessibility. We ask everyone in the room to please sign in at the registration desk if you've not done so. You were also given a name tag. This will be really important that you keep this name tag over the next 3 days because it'll help move you in and out through security much quicker. Lunch and breaks are at the discretion of the chair. And for the panelists, there'll be a shuttle, as there was this morning, to take you back to the hotel this afternoon, and then on the last day to help you get either back to the hotel or to the airport. We want to thank each of you for your agreeing to serve on this panel. It's been a pleasure to work with you, and each of you have been very responsive to needs when we've asked you for information by deadlines, and I certainly appreciate that very much. If you have any needs, please ask anyone at the registration desk and they can try to help you. Thank you very much.
Thank you, Mary. Next slide, please. So this morning and the first part of this afternoon, we will hear from those who designed the study and consultants and experts in subject matter to go over that. In the middle of the afternoon, we will then hear from public comments. Speakers are limited to 5 minutes. We have 5 speakers who have signed up providing public comments this afternoon. And after the public comments have been made, we will then hear from our panel 1 reviewers. And so we'll leave this slide up here for a bit. Could you go to the next slide? Thank you. So this is just some comments or points about the oral comments. Again, 5 minutes per registered speaker. If there are more than 1 speaker from a single organization, then they would share that time. We ask the speakers go to the podium, introduce themselves, and state their affiliation. As I indicated, we have registered speakers for session 1 today and for session 2 tomorrow. So could you go back to the previous slide, actually? Back 2 slides. There, we'll leave that up for now. So we will move into the program now, and I would ask Dr. Chad Blystone to begin the process. Thank you.
Okay, good morning. Here we go. I'm going to provide you with the charge today for the Panel 1 review. Just a little bit of background before we get started. For many years, the NTP has conducted rodent cancer and rodent toxicity studies on agents of public health concern to identify potential hazards for human health. The methods, results, and NTP conclusions as levels of evidence for carcinogenic activity under the conditions of the specific study have been written up in NTP technical reports. We're going to be reviewing 2 draft technical reports over the next couple of days. The first will be the toxicology and carcinogenicity studies of B6C3F1 mice exposed to whole body radiofrequency radiation at a frequency of 1900 megahertz and the modulations of GSM and CDMA used by cell phones. Following the review of the mouse report, we'll move on to the rat report, which we exposed HSD Sprague-Dawley SD rats to a frequency of 900 megahertz under similar modulations of CDMA and GSM. And as you've heard and alluded to, it's been alluded to, due to the complexity of these studies and the uniqueness of them, we'll be reviewing the exposure system. And so the panel for today will be assessing the reverberation chamber technology that was used for evaluating the effects of cell phone frequency, radio frequency radiation exposure to the mice and rats that are in these two reports. And with that, happy to take any questions before we get started.
Yes, thank you. Do any of panel one or any of the panel members have any questions for Dr. Blystone regarding the charge of the committee? Seeing none, we will move on. Thank you, Chad. To Dr. Michael Wyde. Mike.
All right. Well, with all the administrative items out of the way, I want to go ahead and get started on the science. As John said, this has been a long time coming, so I want to thank everybody for coming today. We look forward to lots of discussions over the next 3 days. I'll be giving a couple of talks today. I'll start with this one, which is really just a background and kind of the history of how we ended up where we are today. So to give you an overview of my talk, the first thing I'll talk about is cell phones themselves and the role of radio frequency radiation, why we're concerned with radio frequency radiation. I'll talk about the nomination itself and what we did in those early years, looking at the evaluation of the state of the science and the research that was ongoing at the time. I'll talk a little bit about some of the issues that went into selecting this reverberation chamber exposure system. Again, I'll touch on some of these things. A lot of the concepts that I'll bring up will be further detailed in the talks by Dr. Capstick, both of his talks as well as Dr. Ladberry's talk later this afternoon. I'll talk a little bit about building the facility itself at ITRI, and I'll finish up with talking about the validation that NIEHS did, as well as getting into the toxicology studies that were designed for this radiofrequency radiation program. So when we think about radiation in general, most people think about ionizing radiation, which is on the right-hand side of this screen here. We think of nuclear radiation, we think of nuclear bombs and nuclear energy. However, what we're talking about here with non-ionizing radiation is at the other end of the spectrum, down with smaller wavelengths and much less energy. This is below the visible light spectrum. This is also below the frequencies that microwaves use, but it's above the 60 hertz that are used in power lines. So, as I mentioned, cell phones use radio frequency radiation. This non-ionizing RFR, which I'll be referring to radio frequency radiation throughout the talk, to communicate between a fixed base station and mobile users. This transmits, and cell phones use modulation and encoding schemes to convert analog information like our voice and data into digital, compress it, transfers it, gets it to the other end, and converts it back. This is all done at carrier frequencies, typically range between the 800 and 1900 megahertz frequencies. These are typically the 2G, 3G technologies. Some of the latest 4G LTE technologies actually utilize frequencies up to 2600 megahertz or 2.6 gigahertz. I have to point out here that there's two main technologies that are used in the U.S., especially at the time that these studies were started. The main modulations that were used at the time were code division multiple access, or CDMA. This is typically understood as the network that Sprint and Verizon use. There's also the Global System for Mobile Communication, or GSM. This is typically the networks that AT&T and T-Mobile use. So when I talk about CDMA, I need to point out here that CDMA is more of a generic term that refers to several different technologies. In these studies, we specifically looked at the IS-95, also called CDMA-1. And again, Dr. Capstick will talk a little bit more about this in his talks. The U.S. Food and Drug Administration nominated cell phone radio frequency radiation emissions to the National Toxicology Program back in 1999. This nomination was based on widespread exposure at the time, and there was expanding human exposure. I'll go into this in a couple of slides to show exactly how much the usage has increased over the last 10, 15 years or so. At the time, even somewhat now, there's little known about the potential health effects of long-term exposure to radio frequency radiation. Exposure guidelines have been based on protective limits from acute studies where we saw injury, or where injury was seen from high levels of RFR, which is potentially related to thermal effects, because we know that at high levels of radio frequency radiation we can induce heating that causes tissue damage. Sufficient data at the time was a long way off from humans to definitively answer these questions. These were the bases for the nomination to the program. As I mentioned, there was insufficient evidence in humans. There was epidemiology studies that were being conducted and were being reported at the time. But at the time, the epidemiology studies might not have reflected some long latency periods, and even to this point, they may not necessarily reflect long latency periods of brain tumors and other types of tumors. In 2000, the February of 2000, shortly after this nomination came to us, FDA released a statement, and this statement says that there's currently insufficient scientific basis for concluding either that wireless communication technologies are safe or that they pose a risk to millions of users. And in fact, if you look at it worldwide, this is billions of users. As I mentioned, cell phone radio frequency radiation usage, or cell phone usage, has increased quite dramatically. When these studies were first designed, or when this nomination first came to us in 2000, there were approximately 100 million subscribers in the US. 5 years later, there was approximately 200 million. So in 5 years, the number of subscriptions doubled. In 2010, there were approximately 300 million subscribers. And according to a recent Pew Research poll, 95% of adults in the US own a cell phone. That's a lot of people. In 2016, there were actually 395 active wireless subscriber connections. This exceeds the number of people in the United States. There's only 325 million people in the United States. And in fact, if you think about that, 40 million of those people are actually under 10 years of age. So there's likely 270 million or so that would actually count, that could actually own cell phones. This is an interesting infographic. We could probably spend a lot of time on this, but really what I want to point out is a couple of things. It's estimated now that over 5 billion people worldwide actually are using cell phones. These are unique users, not counted twice. As I mentioned with the US, there obviously, if there's more subscriptions than there are people, there have to be multiple subscriptions per person. As you can see again here, this is on a worldwide basis, but you see back around 2000, worldwide there was about 1 billion people, and as we come up here to 2017, there's about 5 billion people worldwide. So this was a five-fold increase in the last 20 years or so. The regulation of RFR is actually shared jointly by the Federal Communications Commission and the Food and Drug Administration. The FCC is responsible for the devices themselves and assigning the bandwidth. The regulations for the FCC are based, as I mentioned, on injury from thermal effects in acute studies. May not be necessarily protective against long-term exposure in humans. The FDA has jurisdiction over the health effects of radio frequency radiation, and this is under the 1968 Radiation Control Health and Safety Act, which gives them jurisdiction. And the FDA cannot mandate the cell phone industry to provide data on health effects. This is one of the reasons that this came to us. So when this first came to us, in 1999 or so, the first thing we had to do was kind of wrap our head around this issue. The first thing we did was to evaluate the literature, things that were done. We also looked to determine what work was already underway. And at the time, as I mentioned, there were several large-scale epidemiology studies. Probably the largest at the time was the interphone study in humans, which has since been reported. At the time, there was designs underway for what's called the Perform A study in animals. This was being designed in Europe at the time. This project consisted of 6 long-term studies in rats and mice at 4 European laboratories. The staff from NIEHS or NTP and NIST were able to provide input on this Perform A study design, and then we were waiting for the results. In the meantime, we established collaborative research partnerships, as Dr. Bucher mentioned, with the National Institutes of Standards and Technology in Boulder, Colorado, as well as ITIS Foundation in Zurich, Switzerland. And we identified a study laboratory of ITRI, as Dr. Bucher mentioned, in Chicago, Illinois. So historically, one of the main concerns for exposure to cell phones has been effects in the brain. Obviously, because cell phone users use the cell phones close to their head, there was concern more so for the brain than perhaps other organs. In the Interphone study, as well as some other studies, there's been some identification of tumors in humans that may be associated with exposure. And in long-term heavy cell phone users, there's seen this potential association between exposure and the development of gliomas and acoustic neuromas, which are also referred to as vestibular schwannomas. In the literature, when you look at the literature, there's a large number of studies that have been published in the literature reporting biological effects of cell phone radiofrequency radiation in cell cultures as well as in vivo and different types of laboratory animals. And these studies include different endpoints, including genetic toxicology, immunotox, changes in gene and protein expression, oxidative stress, which is believed to maybe be one of the mechanisms by which RFR causes some of its effects. Also, some people have looked at cell proliferation and apoptosis, as well as permeability of the blood-brain barrier. And these studies have shown mixed results. Some of them have been positive and some have been negative. Overall, the animal studies have not consistently demonstrated increased incidences of tumors at any site associated with exposure to RFR. However, it's possible that these negative studies have yielded false negatives in the sense because of some of the limitations that these studies have had. Some of the limitations that were identified were that some of the studies had only a single dose, and in toxicology we like to see a dose response. Some of the exposures were inadequate. The levels were much lower than levels that were reported to show nothing in other studies. In a sense, some of these studies were poor quality as far as their design. A lot of the studies had limited exposure durations as far as the number of hours per day. Some of the studies were limited to just 2 hours a day, some limited to just 4 hours a day. And some of these effects in these studies were stress-inducing because of the way that the animals were housed. Also, some of the studies looked at a shorter number of weeks as far as the duration of the studies, which made it inadequate to evaluate the carcinogenicity. A lot of these studies focus just on the brain, which is good if you're looking just at the brain, but for our hazard identification studies, we're interested in looking at the whole body, looking at any type of effects that may occur between radiofrequency radiation and any other tissues. I think that's especially important as years have gone by and users have started to use the phone less against their head and have used Bluetooth, wireless or wired headsets. They're not actually eliminating their exposure, to just relocating it to some other part on their body where the phone itself would be as opposed to up against their head. So these the primary limitations of these previous studies really were focused around the exposure system itself and how the animals were exposed. As I mentioned, some of these exposures were under stress because of the way the animals were housed and restrained. So the previous exposure systems that had been used up to that point were considered carousel or some of these Ferris wheel type of exposure system. And as you can see here, I've given an example of one of these Ferris wheel types of exposure systems. The animals go into these tubes around the edge here. The antenna is in the middle, and therefore you can see that each of the animals is exposed to a similar field, they're equidistant from the source of exposure. And therefore, there's very consistent exposures between the animals. However, each of the animals needs to be in these tubes and restrained and this is stress-inducing, and so you have to limit the number of hours that the animals are exposed. So the NTP set out to design an appropriate exposure system that addressed some of these limitations of these existing animal studies. And to do that, we incorporated the help of NIST and NIEHS, but first we thought about some of the considerations that would go into the design of these studies, and some of the things that we had identified in other studies that we wanted to make sure were addressed in our studies. Firstly, we wanted to make sure that the exposures, at least in rats, began in utero. This kind of mimics the human exposure. Pregnant women are talking on the phone. There's cradle-to-grave exposure. We wanted to make sure that the animals were unrestrained and individually housed, because I had mentioned before the stress issue. We wanted to make sure that the animals were exposed to a uniform field, and that the exposures were for at least a minimum of 6 hours a day. And as you can see, our exposures ended up being about 9 hours a day. We wanted to make sure that we could expose at maximum power levels at which the animal was able to thermoregulate. We wanted to make sure that we were in what previously was referred to as a non-thermal range, where we were not increasing the animal's body temperature by excessive levels. We wanted to also use intermittent exposure. There was some information at the time that it may be the intermittent use of cell phones that would be likely to cause these effects. So we wanted to make sure that there was intermittent exposure. There were several other reasons for performing this intermittent exposure, which we'll talk about later. And also we wanted to use the frequencies and modulations that reflected those in use at the time and continue to still be in use. These were the 900 and 1900 megahertz. In the U.S., it's centered more around 850. In Europe, it's more closer to 900 megahertz. And the 1900 megahertz is used in the U.S. And as I mentioned, we wanted to look at the technologies that were in use at the time. The CDMA, as I referred to as IS-95. This was a 2G technology that was available at the time. And the GSM modulations, which is more of a 3G technology. And we'll get more into the generations or the Gs as Dr. Capstick will talk about that in his talk later this morning. We also wanted to evaluate effects of RFR in all tissues, as I mentioned. We didn't just want to look at the brain. We wanted to do, for hazard identification, we wanted to look at a dose response up to maximally tolerated doses to apply this to a toxicology study. So as I mentioned, and as John mentioned, we worked with NIST. And the first thing that NIST did was to test the feasibility of reverberation chamber exposure system. This, on the bottom right here, is a picture from some of the early studies that were done at NIST. This was conducted under interagency agreement with them, and we determined, or they determined, I should say, important parameters for the development of the reverberation chambers. They also demonstrated that there was a uniform field, and that the specific absorption rate, or the SAR, was also uniform. And this SAR is a measure of absorption of radio frequency radiation by the animals. So the big question is, what is a reverberation chamber? And I'm just going to touch on this because Dr. Capstick will go into great detail regarding the design, and he'll show lots of pictures of the reverberation chambers themselves. So basically, the reverberation chamber is a large shielded room that has an excitation antenna which emits radio frequency radiation, and a paddle or a fan or a stirrer, we could call it, that spins and creates a homogeneous electromagnetic environment within the chamber. The field exposure is from all directions because of the reverberation of the signal, and is for all polarizations. Now, field variations occur over time, but over time and space, the average field is uniform over the large volume of the chamber itself. And one of the benefits to this approach is that field distributions can be well characterized and easily monitored and measured. So at the same time that we were working with NIST, again, was working on modeling whole body average specific absorption rates, or SARs, and organ specific SARs. Again, this will be in Dr. Capstick's second talk this morning. And with that work, they evaluated specifically the frequencies 900 and 1900 megahertz. And what they found in some of what they found was that there was a considerable difference in the whole body average absorption efficiency between mice at 900 and 1900. And we found that the greatest uniformity of absorption or exposure was for the rats at 900 megahertz and the mice at 1900 megahertz. And again, Dr. Capstick will go more in detail about this in his talks. Next, it is foundation built and tested prototype chamber based on the technical parameters obtained and optimized by NIST. And then, when all of that testing was done, it is constructed 21 reverberation chambers in Switzerland. There was a separate, the way that the reverberation chambers work, obviously the chamber itself can only house one exposure level. So each chamber had a specific exposure level and a specific modulation, either GSM or CDMA. So to accommodate these studies, we needed a GSM low, medium, and high chamber. We needed a CDMA, low, medium, and high chamber, and we had one control chamber. It was a sham chamber. Everything was the same in this chamber except for the fact that there was no RFR that was being emitted into the chamber. So everything else was identical except the fact that these animals did not receive RFR. This control was used as a non-RFR control for both the GSM and CDMA exposures. So as I mentioned, there were 7 chambers needed for the mice. Now for the rats, due to marked weight differences between males and females as they grow, there's a significant difference. We needed to use separate chambers for the male rats and female rats because of the difference in sizes. SARs are based on body weights, so if you put males and females together, you would be underexposing males and overexposing females, and nobody would be exposed at the actual SAR that you were trying to expose at. So therefore, there were 7 chambers that were required for the male rats and 7 chambers required for the female rats. In total, this is 21 chambers. And again, the male and female rats each had a common control that served as a control for both CDMA and GSM. These chambers were then shipped to ITRI in Chicago, and Dr. Capstick has a really great progression of photos demonstrating the size and scope of the effort that went into actually getting these chambers from Switzerland into ITRI and actually functioning. I won't steal his thunder too much, but this is a final picture of what the facility itself looked like. Here's a picture of the facility, although this is only 9 of the 21 chambers, so you can get an idea of how large the exposure facility really was. On the left, this is a picture inside the chamber. This is one particular chamber. And as you can see here, these are the stirrers. This is a horizontal stirrer and a vertical stirrer, which is back behind here. And again, Dr. Capstick will talk more in detail about the purpose of these stirrers and how that was determined. On the right-hand side, we see this chamber loaded with the 2 cage racks, and as you can see, these chambers were designed basically only for the exposures of animals. There's no room to get in here to do any animal husbandry or anything. These racks had to be pulled out, and animals, the husbandry had to be done outside these chambers when the chambers were full. So next I'll move into the validation and the toxicology studies themselves. So as I mentioned, NIST conducted a third-party validation of the exposures in the chambers. They did this several times. They came out once at the beginning, once the facility was set up to validate these exposures. They returned again after our 28-day studies and before we started the 2-year carcinogenicity studies. And then they returned at the end after the 2-year carcinogenicity studies and conducted validation at that point as well to measure the exposures to make sure that we were still where we expected to be. And again, Dr. Ladbury will talk about this in greater detail this afternoon in his talk. So NIST confirmed the measurements for the chamber RFR reported by the actual system itself. And all environmental and exposure parameters during the study were not only recorded by ITRI, but also it is, and they were able to monitor the studies from Switzerland as the studies progressed. Now, the toxicology studies themselves, which we'll be talking mostly about tomorrow and the next day, these studies were designed in 3 phases. The first phase we'll actually talk about, it'll be the last talk that we'll talk about today. This was a 5-day thermal pilot study with exposures of SARs between 4 and 12 watts per kilogram. Again, we'll talk about this afternoon. Then tomorrow and the next day we'll talk about the 28-day studies. Tomorrow we'll talk about the studies in mice. And then on Wednesday we'll talk about the studies in rats. Just to give you an idea about the designs themselves, in all of these studies, the daily RFR exposure in the chambers was for 9 hours and 10 minutes of actual exposure. This was done over the course of 18 hours and 20 minutes of the day with a 10-minute on and 10-minute off cycles. This allowed the animals 10 minutes break, and again, this was the intermittent exposures that we discussed. And while the exposures were only 10 minutes for each of the modulations, the system itself was running constantly in the sense that it would be running 10 minutes for the GSM cycle, and then it would turn off the GSM cycle and turn on the CDMA cycle, so we could reuse the amplifiers and not have to double up on signal generation. And again, as I mentioned, these studies were conducted in rats for both modulations at 900 megahertz, and in mice for both modulations at 1900 megahertz. We've actually started to report some information. A lot of you are familiar with some of these papers. These were provided as part of the material that was given to you for this review. The first 2 manuscripts that were released were from These are Capstick et al. And the Gong et al. Papers. The Capstick et al. Paper talks about the exposure system. This is what Dr. Capstick will be talking about in his next talk. The Gong manuscript talks about the dosimetry, which will be Dr. Capstick's second talk. And the third manuscript, which is now in press, is the results from the thermal pilot studies, which we'll be talking about later today. And as you know, and as John mentioned, we released a partial findings report in May of 2016, looking at the 2-year responses in brain and heart. And with that, I'll take any questions.
Thank you. We now have some time for questions from the panel. Yeah.
Yep. When you were designing and knowing that this was going to take a long time, did you build in any flexibility in any part of it? And what I meant is that in your design when you started out, how much flexibility did you have in design? Maybe this will come up later, but knowing that it's going to be over a long period of time, I'm just curious about flexibility in design.
I'm not exactly sure what.
For example, if something came up in technology, and that you thought was really important, was there anything built in early on to say, okay, we can change that, and where those type of things?
Right. Now, I think Dr. Capstick might talk about this a little bit more later, but to some extent we were locked into the technologies that we were using, the signal that was generated. So as newer technologies came out, it would be very expensive for us to switch up to go to 4G technologies, to change frequencies, to do things like that. So there was some flexibility built in as far as endpoints and the designs of the tox studies themselves, but most of the parameters of the reverberation chambers themselves were pretty much locked in once we had selected those designs.
Yes.
Mark Klein, Wake Forest. The slides are very helpful, and I would ask for a copy of them if we could get them. I have a question about the infographics used in the slide presentation. Note they're from .com domains, and I would worry a little bit about the provenance of that information and its accuracy. So I would just ask you, was that information peer-reviewed?
No, that's most of what we have is from surveys, and I think it's difficult to get a handle on how many Americans use cell phones or how many people worldwide. And I think they used to use the metric of how many subscribers, and they would talk about penetrance. But once it got beyond the point where there was more subscriptions than there were people, it was hard to say, how could you have more than 100% of people? But again, most of this stuff comes from, I think, surveys of people in literature, like the Pew Research survey. So I think it is a little more difficult to get some of that information. You would need to get that information from the actual service providers.
Okay. And my last question, I may be jumping the gun here, but I would like at some point to know if the animals could perceive when the apparatus was on or off, and what kind of perceptible emissions there were associated with the exposure.
Right. Well, I think we could talk about that as we review some of the studies. It's probably something left for probably when we do the actual review.
I have a question for you, Dave Eaton. Animals have biological effects from circadian rhythm and circadian rhythm disruption with light cycle, and I'm wondering how you coordinated your cycling of exposures, where there was a 6-hour period where there was no exposures, how that was coordinated with the light cycle, because rats and mice are nocturnal animals, and I'm just curious as to how you coordinated that.
Right. Yeah, actually, one of the reviewers had asked about the times of the actual exposure, and we'll be adding those into the report itself. But there were 2 husbandry periods, one in the morning, I believe from 7 in the morning until about 9 or so, and then there was one in the afternoon. So these husbandry was done during the earlier morning and mid-afternoon. So the exposures themselves went on throughout the night and the other periods of time that they were exposed. So we didn't necessarily take circadian rhythms into account in this study.
Yes, Dr. Lin.
I have a couple of clarification type of questions. You mentioned that the control and exposed animals were exactly the same, except the controls did not have any radio frequency exposure. The question has to do with the mechanical noise, especially you use the term paddles or mold stirrers. Those are mechanical devices. One reason for that is for you to distribute the various kind of modes. But at the same time, I suspect there are some mechanical noise that's being produced as well. So my question is, for the control chambers, were the mold stirrers turned on or were they off?
Yeah, the stirrers were turned on in the control chambers as well.
And did you know note what kind of noise the stirrers might have produced?
I'm not sure about the stirrers themselves. Dr. Capstick will get into some of the noise issues in his talk, but there was some noise that was heard at the high GSM exposures, and that was normalized that was recorded and normalized across all of the chambers. So the noise that would have been heard in any of the 1 chambers would have been equalized across all of the chambers.
Okay. And the follow-up question has to do with the comment that the GSM and the CDMA were applied in 10-minute intervals. I think you also seems to imply that they were implied sequentially. Is that correct?
It alternated between, the animals that were exposed to GSM were exposed for 10 minutes, and then while they were resting for 10 minutes, the CDMA animals were on for 10 minutes, and then it kept switching back and forth between the GSM animals being exposed and the CDMA animals being exposed.
So when the animals in a given chamber were exposed, they were basically exposed for 10 minutes, rest for 10 minutes, then exposed to another modulation.
No. It was all the same modulation. So if animals were exposed to GSM, they were exposed to GSM, 10 minutes on, 10 minutes off, 10 minutes on, 10 minutes off, only to GSM. And then the animals that were exposed to CDMA were exposed 10 minutes on, 10 minutes off, cycling just to the CDMA.
So in different chambers?
Right, totally different chambers. And that's why we had 21 different chambers, because for the GSM, those could only be exposed to the GSM signal, and for the CDMA, those could only be exposed to the CDMA signal. And for the
Thank
rats,
you.
there was only 900, and the rice, it was only 1900.
Good.
Yes, Dr. Barnes.
Frank Barnes, what was the variation in between chambers statistically? In other words, how close to the same exposures did you get? What sort of variation did you get? This may be premature to ask.
Yeah, I think that's something that Dr. Capstick will address in his talk and the next day.
Fine, we'll take that later then.
Okay.
Any other questions from the panel? If not, we will move on. Thank you, Michael. Dr. Miles Capstick.
Good morning, everyone. It's a pleasure to be here and talk about the exposure system that we designed some time ago. So just work out how this works. There we go. I'm going to give you a bit of an introduction, both to the communications standards and signals that were used throughout the study, the reverberation chambers themselves and the sort of exposure environment that provided to the animals. Talk about the chambers and the characteristics that were required of those chambers for the NTP study. Throughout the study, we wanted to obviously to expose the animals for long periods of time, so we needed to supply water and food to the animals, and doing that is has its challenges. So I want to focus on that for a while. Talk about how we monitor the environmental conditions, both from the electromagnetic field point of view and the temperature, humidity, noise, light perspective, and how they were logged, and then how we could post-process that afterwards. And then a little bit about the chamber construction and the installation at the facility at ITRI, and I can just give a brief summary. So the requirements for this study were that we would have 3 exposure groups plus a sham exposure group with approximately 100 animals per group. And the aim was to have as long an exposure per day as possible. So theoretically it could have been 24 hours per day, but you have to perform animal husbandry. So there was a pause in the morning and there was a pause in the afternoon where staff could go in and perform those duties. And the main reason for that was that in the previous studies, such as Perform A, it was determined that the short periods of time that the animals were exposed every day was insufficient, because the animals were constrained in a tube and then placed into the exposure system. So during the exposure period, there was no water or food available. So that limited the total exposure time per day. And from that perspective, we needed the animals to be unconstrained, and as soon as they're unconstrained, then we need particular requirements from the radio frequency environment, so we can maintain a relatively constant exposure of the animals as they move around, as they change their posture. And back before I was ever involved, NIEHS proposed that reverberation chambers would be a good environment, and made these feasibility studies that you saw in Dr. White's slides just before. So, the exposure system requirements for studying these non-thermal or minimally thermal effects were the ability to expose large number of animals, rodents, to expose to a relatively high dose or high specific absorption rate for up to 20 hours per day. It ended up being 18 hours and 20 minutes. The animals to be unconstrained, to be housed in standard laboratory cages, where the minimum cage sizes are obviously defined in the animal husbandry standards for humane care. Food and water to be available on demand. We required excellent field, or more importantly, SAR homogeneity across all the animals in a given exposure group. we would perform detailed dosimetry, both numerical and experimental. So what we have is we have the animal, it's exposed to a field which is coming external to the animal, and that external field induces fields internal to the animal. And it's the relationship between the external field and the internal field that is the subject of this dosimetry. And we require the possibility to determine if there's a dose response through 3 different exposure levels, including plus the sham control. And the idea was that we would produce the exposure system and then it would be verified by a third party, which in this case was NIEHS, to determine that it was operating in the way that it was demanded. So a little bit more about exposure groups. So there's a couple of ways of quantifying the exposure. You can quantify in terms of the incident field, but the incident field doesn't tell you everything about the exposure, and you can quantify in terms of the induced fields or the specific absorption rate, which specific absorption rate is the amount of power that is absorbed per kilogram or gram of tissue. And the SAR is a function both of this incident field, and the incident field has various properties. It has amplitude, it has direction, it has polarization, phase, and all these come together to characterize the overall incident field, and also the body mass of the animals and the body shape of the animals. So when we look at the data from historical NTP studies for rat weight and mouse weight, and we can see we've got age in days along the bottom there. So this is for the typical 2-year study. Clearly the rats, the males and the females are very different in their weight. The males rapidly get much heavier than the females, and we see that it ends up that they're approximately twice as heavy as the females at the end of the study. So given that the overall specific absorption rate is a function of body mass, if we expose these animals to the same field in the same chamber, then we get very different specific absorption rates in the animals. So they need to be housed in separate chambers. Whereas when we look at the mice, the body weight follows a very similar curve over the lifetime. So they could be exposed in the same chamber. I mean, plus the fact the mice are obviously much smaller than the rats, and the requirements for the size of the cage is much smaller for a mouse than a rat. So fitting twice as many mice in a chamber compared to rats is also possible. And physically, the chamber would have had to be much, much larger than they were if we were to house the required numbers of male and female rats in the same chamber. So, at the time, we studied all the information relating to exposure and what might be important in terms of exposure. And we used that as a rationale for the selection of the exposure in terms of frequency, modulation, and the low frequency envelope. So I'll just go through what those mean so we fully understand what I mean by those terms. So it was postulated that the carrier frequency is not the most biologically important thing, but it's mainly relevant for the coupling of the fields to the animal. So if you have a smaller animal, then a higher frequency couples more effectively, and a larger animal, a somewhat lower frequency, will couple more effectively. That the signals should contain the maximum spectral power of all modulation components generated by the handsets, as well as by base stations, but primarily in this study handsets. And those low frequency spectral power modulation components are due to the native modulation of the carrier to convey the information, but also the power control that's implemented by the network to maintain a good connection to the network. And so if you have something like human exposure and a typical mobile phone, back in those days, a mobile phone was used for making voice calls. You held it next to the head and it exposed the head relatively locally. And the maximum exposure was considered over a small volume. And but where that volume might be 1 or 10 grams. But when you look at a few tens or thousands of cells, then it could be considerably higher. So the peak SAR is bigger than that spatially averaged SAR. There was also several authors that emphasized the importance of on-off cycles, and that's why we chose this on-off cycle, 10 minutes on, 10 minutes off, with interleaved GSM, then CDMA, GSM, CDMA, and that way we could reuse the amplifiers. So the consequences of the exposure selection were that we selected frequencies that were commonly used for mobile communications, that gave good coupling and relatively uniform exposure in the animals, and combined modulation and power control characteristics to maximize this ELF spectral envelope. So just to give a little bit of insight as to what I mean by the ELF spectral envelope. So as a cell phone and a user, as you move through your environment, the distance to the base station changes, but also if you're in an urban environment, you get reflections off buildings, and those reflections can combine to give constructive interference or destructive interference. So the signal level received increases and decreases. Likewise, the signal level that's received at the base station also increases and decreases. And what the network does, it sends information back to the handset and says, your signal is decreasing, please increase power, or your signal is increasing, please decrease power. And we can see a typical characteristic here, where with time, you set off at a relatively low level, and then the power steps up, and then can step back down. This is for GSM, where you have up to a 1,000-fold difference in power level between the highest and lowest power levels. And you get a similar sort of arrangement with the CDMA signals, where the power is stepped up and stepped down to maintain a constant signal at the base station. Also, if you can turn the power down of the handset, it increases the battery lifetime of the phone, and that's also beneficial for the user. And it causes less interference to all the surrounding cells, so the whole network works better if we can minimize the amount of power radiated from the handset. So, if we just take the case of GSM, in GSM, the modulation envelope is constant. So if it was transmitting the whole time, the handset, the power output, and it didn't move within the environment, it would be constant. But GSM uses what's known as time division multiple access. So to have multiple users on a single base station, it gives each user a section of time. And it can support 8 users on a single base station, so each user gets 1/8 of the time. So it transmits for 1/8 of the time, goes off for 7/8 of the time, transmits for 1/8 of the time. So you then got this multiple access on-off modulation superimposed on top of it all. And then we have this power variation, which is then superimposed upon all that. So there's all these different aspects to the modulation. The modulation itself, the access technology, and the power control. So if we look at current cell phone bands that are in use here in the USA, we have still some CDMA 1 or IS-95 still in use down here in the 800 to 850 megahertz region. It's also in use at 1900 megahertz. There's a little bit of GSM. We then have some 3G standards, CDMA 2000 and UMTS, also in the 850 and 1900 megahertz region. So UMTS is also a CDMA standard. And then moving on to 4G and LTE, similar frequencies in use again, down in the 800 to 850 and a little bit lower as well, but also higher frequency bands. To go into the signals that we used in the studies in a little more detail, if we take both of them here, we looked at GSM uplink and CDMA uplink. So they have different modulation characteristics, quadrature phase shift keying and Gaussian minimum shift keying. I'll talk a little bit about their characteristics and their access technologies. But basically the CDMA occupies a much wider bandwidth than the GSM and can support more users than a single GSM base station. And basically the data rate for the CDMA standard is relatively low, only 9.6 kilobits per second. And it's a similar sort of data rate, but here, but split across the users. So you don't really appreciate how much of that data is related to the voice channel. To try and talk about the access methods in a little bit more detail. So it's basically split into three different types of access technology. There's frequency division multiple access. So this was equivalent to what we had with the old analog phones, the so-called first generation of phones. Not very many users back then, but basically they split the frequency into lots of channels, and each channel was used by one user for the duration of their phone call, and they had sole use of that channel. And this channel might have been 12.5 kilohertz wide, something like that. So relatively narrow channels. We then have time division multiple access. This only became possible once we had digital voice standards available. So this was analog phones, and now we moved to digital phones. Here we have wide channels, but now each user is allocated a time slot in the time domain. So you have to get this on-off modulation of the carrier due to the multiple access method. And the final method is code division multiple access. And here all the users use all the bandwidth all of the time. And the way they do this is you generate what's known as a pseudocode. The pseudocode is like a noise-like signal, and it's very broad. So you have a relatively small amount of information, and then you spread it across a wide frequency range. So to all the other users, it looks like a little bit of increase of noise. And at the base station, if you then multiply it by this pseudo noise again, you can reconstruct the signal, rejecting all the other users, and get it back. So they're basically on top of each other, and they don't really realize they're there. So GSM uses 200 kilohertz channels, constant envelope, so there's only phase changes. So to represent in the binary numbers, you advance the phase or retard the phase by 90 degrees over each symbol, and then you end up with a constant amplitude, because all that's changing is the phase, not the amplitude. And that fits into the 200 kilohertz bandwidth by using Gaussian filtering. And then again, as I said before, we have this on for 1/8 of the time, off for 7/8 of the time. And if we look at the time scale here, we're talking milliseconds, with each base station having up to 8 users. So we have a high peak power, and the average power is 1/8 of the peak power. whereas IS-95 or CDMA1 is quite different in its characteristics. Don't want to go into too many details, but we now have a 1.25 megahertz channel, so it's about 6 times as wide, a little bit more than 6 times as wide as the GSM channel. And we spread, so we have the energy equally spread across that channel. We have the data coming in here, and then we spread it with this pseudo noise, and the signal that we end up with looks like this. And now, whereas before we had variations on the millisecond time scale, here the variation is on the microsecond time scale. So these amplitude variations, they're not on and off, but they're varying smoothly with time. But the rate of change is about 5,000 times faster than that of this on-off pulsing of the GSM signals. So how does this relate to the signals that are in use now? So moving from IS-95 or CDMA1, one of the first 3G standards was IS-2000, and it had exactly the same signal characteristics. So the chip rate was the same. It's just, whereas with IS-95, the data rate was limited to 9.6 kilobits per second, and the so-called processing gain was 128. Moving to CDMA 2000, they could have variable bit rates or data rates, and with the so-called processing gain between 256 and 4, so we could have up to 300 kilobits per second transmitted over that same channel. But the characteristics of the signal was essentially identical to that we see here. So CDMA 2000 was, as I say, one of the first 3G standards. That evolved into wideband CDMA and UMTS, depending on who the provider of the technology was. And they basically went for a chip rate which was about 3 times faster than the chip rate that was used for IS-95. But again, the signal characteristics, due to the modulation methods, were similar. It's just now the variation was happening a bit more than 3 times faster than we saw with this. So all these CDMA standards have very similar characteristics in terms of their variation in the modulation envelope. Superimposed on that is then the envelope due to the power control. So just to recap how that then corresponds to what we have now with 4G, and how that might pertain to the upcoming 5G standards. So that so we had this FDMA, which was used for the analog phones, then this time division multiple access, where we had both channels and time slots, CDMA, where we had, basically few channels with many users, with their information spread across with these orthogonal spreading codes. And then when we come to LTE, we have what's known as orthogonal frequency division multiple access, where the resource is split into blocks in both in time and frequency. And depending on how much information the user wants to transmit, then they're given different numbers of resource blocks, both in the frequency domain here and the time domain. So if there was only one user and they had an awful lot of data, then basically they could use all these resource blocks. But what normally happens is, rather than being dotted around like this, you might have blocks here, both in the frequency domain or time domain, that are clumped together and allocated to any particular user. So whereas the characteristics of 2G, 3G signals were well defined, the characteristics of both in frequency and time domain of the LTE type signals are variable, and there's no particular characteristic. What we do know is that each time slot is 10 milliseconds, but you might transmit in multiple 10 millisecond blocks, so it's not that it goes on for 10 milliseconds and off, but it could go on for 10 milliseconds, 20 milliseconds, 30, 40, or any multiple of that, and then off for any multiple. So it's now not random, but now controlled by the network rather than the number of users and the data to be transmitted rather than the specific standard. So that's about the signals. Now talk about the exposure environment and how we apply the signals to the animals. So a reverberation chamber has two elements. It has the chamber and it has the mode stirrers, or paddles, or fans, or whatever you would like to call them. So if we just consider the chamber to start with, it's basically a fully shielded enclosure, a metal box where the RF is kept inside the box and it can't escape to the outside. This box forms a resonant cavity. So what do I mean by a resonant cavity? If you introduce energy into that chamber using an antenna, then it will set up particular field structures inside the chamber which can have regular patterns. So here's some field structures that are typical of resonant cavities. So they have peaks and troughs in the field, peaks in E field, peaks in magnetic field, electric and magnetic field at different locations. And because the chamber is big compared to the wavelength, it supports many different resonant modes. And you know, if you had a source at a particular location and with the same frequency, it would always excite the same modes. So you'd have particular peaks and troughs within the standing wave pattern inside the chamber. So if we then put animals in there, you know, peaks and troughs would typically be about half a wavelength apart. So half a wavelength at 900 megahertz is about 17 centimeters, and at 1900 megahertz, 8 centimeters. You would go from peaks to troughs over approximately the size of an animal, something like that. So it would depend exactly where the animal was as to what their exposure would be, and that would be undesirable. So what we then do is we introduce mode stirrers. So mode stirrers are paddles or fans which rotate within the chamber. And before I joined NIEHS, I was at the University of York in the UK, and we had a group that were working on how to design mode stirrers so you got the maximum scattering of the field and could excite the maximum number of modes in the chamber. And that leads to having the best homogeneity in the chamber. And the idea is that you should have no symmetry. All the surfaces should be at different angles with respect to each other, so that as the stirrers rotate, you excite different modes. So we can go from having a uniform mode pattern to having mode patterns that vary with time as the stirrers rotate. So what we use is an antenna inside the chamber. We point it at the stirrer. The metal surfaces of the stirrer scatter that field, and we can end up with complex scattering patterns from those stirrers. And what we want to do is have as large a stirred volume as is feasible without taking up too much volume in the chamber. So to do that, we had a horizontal stirrer here rotating and a vertical stirrer at the rear, which you can just see behind this guard. So the guard there was to stop the stirrer being damaged when the staff put the racks with the animals into the chamber. And these stirrers would rotate during all the exposure periods. They would stop when the staff were going in to do the animal husbandry to avoid any issues with them colliding with them, though it was above head height, so it shouldn't happen. And here you see we've got nice, interesting and complex patterns of the reflected field from the stirrers, depending on the angle. And as they rotate, these reflected fields are continuously changing. So these are sort of antennas we were using. They're somewhat directive. They're known as standard gain antennas. But with these, you could point them in a particular direction, i.e. towards the stirrer, to get this scattered field. And that way, we tried not to point them directly into the volume where the animals were going to be housed. One thing I should say is as the antennas rotate, the stirrers rotate, the field pattern is continuously changing. So if you look at any one point, the field goes up and down with time. So it's temporally varying. So the exposure at any one point would also temporally vary. And I'll go into how we could use that time variation, temporal variation, to mimic the power control of the handset in environments. So the exposure field is one thing. We also need to maintain the animals in conditions where they're happy. So there's requirements for airflow, and NTP requires 12 air changes per hour or 10 air changes per hour, but not to increase the noise too dramatically in the chamber, but also to get that air in without the RF going out. And to do that, we could use tubes, and these tubes were about this sort of long, 50 centimeters, and the diameter was around 60 millimeters. So the diameter has to be less than half a wavelength, and if it's less than half a wavelength, the RF wave, electromagnetic wave, cannot propagate down the tube and therefore is maintained inside the chamber and doesn't escape outside. And we wanted 100 dB of isolation. So that means that power levels in the chamber are 10 to the 10 times higher than the power that escapes. So we didn't have much power escaping from the chamber. So based on this, we came up with a chamber design and then built a prototype. And this was put together inside the labs at our offices in Zurich in the basement. It was brought in pieces because we couldn't fit it through the door, and welded together in situ. You can see the ventilation tubes for the exit air here, and at the rear of the chamber the air came in at the bottom. We've got this special door here which has special features that stop the RF from coming out, and there was ribs welded onto it to maintain stability. There was then requirements for lighting. So NTP says that you should have 40 to 50 foot candles 5 feet above the floor. So 1 foot candle is 10.7 lux. So we were looking at 400 to 500 lux, 1.5 meters above the floor. So in typical lab environment, the luminaries are ceiling mounted, so you have a decaying light level from the top going down to the floor, and the requirement would be met about 5 feet above the floor. We have this stirrer on the ceiling in the chamber, so we can't put lights on the ceiling of the chamber because the light would be modulated by the stirrer rotating, and we didn't want to introduce this light modulation into the environment. So what we needed to do was to meet the spirit of this requirement, if it wasn't the exact word of the environment. And we aim to do that by looking at vertical planes in the centre of the chamber rather than something that was horizontal. Another thing that I think is worth to mention at this point in time, if we look at the light or the colour temperature of a typical animal facility, they use fluorescent lighting, and the colour temperature is in this range, centred on about 4,500 Kelvin. If you put a fluorescent tube inside a reverberation chamber, the high EM fields inside the chamber would cause the tube to light, whether it was switched on or not, and then you would get a field-dependent variation of the lighting, which you couldn't switch off to give daily cycles. So we didn't use fluorescent lighting. We used incandescent lighting, and incandescent lighting has a rather different frequency content to the fluorescent lighting, as you're all aware. So we were down here. So in terms of a specific implementation that we implemented, we put, so the vertical stirrer was here. This was this guard to stop the stirrer from being damaged. This is the volume where the cage racks would be. The smaller one was a mouse rack, the larger one the rat rack, and they were housed here, two side by side, the door over here. And we put luminaries in the corners, here, here and here, pointing in towards where the animals were housed, with 3 bulbs mounted vertically. So we didn't have much vertical variation in the light, but the variation was more towards the centre of the room. And to reach the NTP requirements, we determined that 12 40-watt bulbs were appropriate. So rather than having this sort of gradient from top to bottom, looking at the exposure volume, we had a gradient coming in from the corners to the centre. And here's a picture of the lights when they were installed in the chamber. So that's talked about the airflow, and the airflow, that air coming in, the temperature was controlled and came from the HVAC system. We've talked about the lighting. We've hinted that there was requirements on noise, and we'll talk a little bit more about that in a little while. But now I want to focus on the performance in terms of the electromagnetic fields inside the chamber. So there's different ways we can characterize the performance of a chamber. We can talk about stirred to unstirred energy. We can talk about homogeneity, and we can talk about isotropy. So, in a reverberation chamber, we have these mode stirrers, and the hope is that the mode stirrers are going to cause all the energy in the chamber to be stirred. In reality, you can never reach that. You get most of the energy being stirred and randomized. So if you imagine, if this was our chamber and we had an antenna up in the corner here and a mode stirrer, we could point it towards the mode stirrer. Some of the energy would be scattered by the mode stirrer, but some of the energy would be directly aimed at our test subjects here. And that direct energy is not stirred. The animals or humans or whatever would be exposed to that all the time, and then superimposed upon that would be this energy that was scattered by the mode stirrer. So ideally, when we plot the transmission from one antenna to a second antenna inside the chamber, we've got magnitude moving out from the center and the phase here. So these are complex quantities. If we average the complex quantity, we should end up with the average being 0, i.e. right here in the center of the plot. We can see here, it looks reasonably well scattered across the plot and reasonably well centered on this. If we then average the magnitudes, i.e. just the distance from the center of each of these measurements, and then divide it by the average of the complex quantity, then at 900 megahertz we found that we had about 20.4 dB. So the unstirred energy was 100 times smaller than the stirred energy, which is good performance for a mode stirred chamber. It was a little bit worse at 1900 megahertz, about 50 times the ratio. Now I'll talk about the homogeneity and the isotropy. So this stirred to unstirred energy, if the ratio is very bad, then that means that you're never going to get good homogeneity. But ours was good, so we were hopeful that the homogeneity would be good too. So we took some field probes. In this particular case, there was 4 electric field probes and 2 magnetic field probes, and we put them into this equipment here, and this could move the probes up and down inside the chamber, so we could measure at different points, and then we could move this whole frame around inside the chamber to different locations on a horizontal plane, and that way we could gather information of the field. And we did that over 216 individual points inside the exposure volume, so we only measured where the animal cages were going to be. And we used these field probes are very small. Their effective integrating volume is 5 millimeters by 5 millimeters by 5 millimeters. And these are the sort of results we ended up with. So this is just taking one horizontal plane. Here is the variation for the total E field. So each of the probes measured 3 orthogonal components, X, Y, and Z, if you like. And you can then sum them up vectorially to get the total field. And we also made maps of the individual field components, so the X, Y, and Z components. And from that, taking all the slices, we could build up these homogeneity maps inside the chamber. So this was for 900 megahertz, this particular map here, with the individual planes. The label's got a little bit displaced, so it goes from minus 1.5 dB here to 0 in the center, 0 being the average, to plus 1.5 at the top. And at 900 megahertz, we had a homogeneity of 0.6 dB, and the isotropy. So let me just say what I mean by isotropy. So the hope is that the field impinges upon the animals from every direction equally, and that way, as the animal moves around, changes its orientation in the chamber, rears up, possibly curls up, changes its posture, if the fields are impinging from all directions, then that orientation won't alter the exposure of the animal with time. So we got good isotropy, around 0.9 dB, and the total population range of all the components, individual components, of plus or minus 2.4 dB. If we took the population of the vector sum of the components, then it's obviously less than this. Performance is a bit better at 1900 megahertz, 0.5 dB homogeneity, 0.7 dB isotropy, and total population range is a bit smaller. The reason being, in terms of wavelengths, the chamber is bigger at 1900 megahertz. The wavelength is about half the size. So in terms of wavelengths, it's effectively 8 times bigger. That was in the empty chamber. The empty chamber is, of academic interest really, because the chamber was never going to be empty. We were going to put cages in the chamber, animals in the cages. I'm going to talk about the water system in a minute, but there's also a watering system in there for giving the animals water, and they all can potentially alter that homogeneity and the field structure inside the chamber. So what we did, we put in the 2 cage racks, put into the cages, along with some bedding, some food, these phantoms, which were homogeneous phantoms, approximately a similar weight to the adult animal, filled with a tissue simulating media, so they absorb the same amount of energy as the real animal, though obviously they're not real animals. Put them in the cages. We just threw them in the cages. When I say throw, I mean not violently, but not really considering which orientation they were in. We didn't align them all the same. We just threw them in so that they were reasonably randomly aligned. And then we put in field probes, and we would place them on top of the cage lids. So you have a cage lid, the gap, and then the next cage. And we would move them around inside to different positions. And when we then calculated the homogeneity and isotropy inside the chamber, which is something that NIST also validated, and I'm sure that Dr. Ladbury will tell us about that this afternoon. We ended up with slightly poorer homogeneity, but not dramatically so, and the isotropy is a little bit poorer as well. But obviously the uncertainty, when we only measured 32 as opposed to 216 locations, is somewhat higher. So it could be that it's very similar, really. And again, a bit worse at 1900 megahertz. So I just mentioned uncertainty there. So we did determine the uncertainty for these field homogeneity measurements. So basically we use what's known as a step and measure approach. So we would move each of the stirrers incrementally, stop, let the stirrers stabilize in their position. We would measure, and then we would step them again to a new position. This whole process takes time, so we were limited in the number of discrete stirrer positions that we could measure, and if we had infinite time, then we could have reduced this uncertainty due to the stirrer modulation down to a low level. So we basically had uncertainty related to the calibration of the probes. So the probes were calibrated, traceable back to national standards. So there's absolute accuracy. There's then some linearity in terms of the frequency response of the probe. Linearity in turn for the amplitude response of the probe. They're not perfectly isotropic, so there's some isotropy, uncertainty, and then this modulation, which is related to the fact that we could only do a finite number of different stirrer locations, coming up with an overall uncertainty of about 0.58 dB. So that's around 16% for those not familiar with decibels. The reason we talk about decibels is a logarithmic quantity, and a lot of these quantities are log normal rather than normally distributed. So expressing the uncertainty in terms of decibels or a logarithmic quantity makes sense, but I also appreciate that it's not everyone is familiar with that, so I'll try and interpret as to what it means in terms of approximate number of percent. So they're not equally distributed in a positive direction and negative direction. So we have the stirrers going around. As the stirrers going around, if you take any individual point inside the chamber, its field value goes up and down with time, and it varies, and the variation of those fields can be displayed in a cumulative distribution function. So we have potential to vary from the maximum up here down to something that's 10,000 times smaller, and it can move up and down this curve, and this is actually a Rayleigh distribution of amplitudes. So Rayleigh distribution is a distribution where there's no constant or line of sight element to the signal, but it's all the energy is stirred, and that was what we were aiming for, so that's good. But 0 dB is the average or mean field level in the chamber, so we have variations from this 0 level here up somewhat, a little bit, a few dB, maybe a 4-fold or 5-fold increase on the positive direction, but also some very deep nulls in the signal going down to minus 40 dB here, which is 10,000 times smaller in terms of power level, or 100 times smaller in terms of the field strength, in terms of electric or magnetic field strength. Now, this talks about Qs. What do I mean by Q? The Q is the quality factor of the chamber. Now, the quality factor talks about the amount of energy stored in the chamber, so we introduce energy using the antennas. That energy bounces backwards and forwards, creating these mode structures inside the chamber. So that energy is effectively stored. But over time, the energy doesn't keep increasing and increasing. It's stable, so it's dissipated inside the chamber. And it's dissipated in different elements inside the chamber. So we have the empty chamber here, and we have values for Q in the 7,500 to 24,500 range, depending on whether it's 900 megahertz or 1900 megahertz. But an empty chamber is not so useful. So into that, we introduce various elements. We introduce lights and antennas, and they absorb some energy. We introduced the cage racks. They also absorb some energy. We constructed the cage racks out of low-loss materials, fiberglass profiles, and polycarbonate. The idea being that the aim is not to disrupt the fields in there or absorb energy in those elements. And we can see that the Qs were relatively high. We then put in animal phantoms. These have low Qs. That means they're absorbing lots of energy. So that's good. We wanted the energy to go into the animals. That's the whole purpose of this exposure system. And then there was the bedding and the food and things like the stirrer guide. And ultimately, we end up with different Qs. So this was the maximum number of the maximum size of phantom. But we set off with small animals, and they grow. So what is important is each of these lines represents effectively a different age of the animals, and where they're absorbing different amounts of energy. So we see that the signal statistics that are applied to the animals doesn't change over the whole lifetime of the animal. So we can talk about it in terms of Q, but what's, I guess, more intuitive is what is dissipated in each individual part. So the total power here at 900 megahertz was 422 watts. Maybe I should have normalized it to a nice round number, but I only just thought about that now. 15 watts were absorbed just by the metal walls of the chamber. Stainless steel, the chamber, I forgot to mention that. Anyway, so chambers and everything inside was stainless steel, so it could be washed down and kept sterile. The lights and the antennas absorbed some of the energy, 33 watts. The cage racks, 27 watts. The animals, 310 watts. The bedding, at least while it's dry, probably doesn't stay dry for too long, not very much. The food, the stirrer guide. So in terms of the effective efficiency, we had about, with adult animals, about 74% efficiency. So that's the amount of power going into the animals. In terms of the mice at 1900 megahertz, again, we have part absorbed in the chamber, the lights, the racks. The animals are much smaller here, 10 times smaller than the rats, so they're absorbing less energy. And again, energy absorbed in other things. So with adult animals, we hope to reach about 46% efficiency in terms of the energy that we put in to that absorbed in the animals, giving the exposure. So we've seen we have a chamber that is reasonably homogeneous, but it's only reasonably homogeneous. There is some element of inhomogeneity there. It's relatively small, the bounds of that inhomogeneity, but if we just put a single probe in at some random point to monitor the field strength inside that chamber, then how that relates to the average field in the chamber would be uncertainty within those homogeneity bounds. So by putting in multiple field probes, we get a better estimate, and we can decrease the uncertainty by the square root of the number of probes that we introduce. Unfortunately, probes are expensive, so you can't just put lots of probes in there. So it was decided that 2 was a good compromise. So we could use 2 probes and reduce the uncertainty related to the homogeneity. So in terms of the exposure field uncertainty, so that's the fields we apply to the animals. Then we have, again, the probe accuracy, the frequency linearity, the dynamic range linearity, the isotropy. There we've all seen before when we were measuring the homogeneity. And now we have this term relating to having 2 probes and the homogeneity, and that was around 0.43%. And as we measure the field, we try to maintain it at a constant value, but the field is continuously changing in the chamber, so there is a little bit of variation, and we reckoned we were managing to achieve better than 0.2 dB for that field control. So overall, we had about 0.6 dB uncertainty, which is between minus 13% to plus 15% of the target E field inside the chamber. Moving on, we have these temporal variations in the field, and I said that we were going to show how these could be then tuned to give some physical meaning when compared to real exposures from mobile phones. So the idea was, we've got this variation. If we, say, take our mobile phone and we use it in the car, obviously not while driving, then as we move through the environment, we move from one base station to the next base station, and we also have multipath, we have reflections off buildings. This all acts to vary the signal that arrives at the base station, and then the base station acts to try and control that, to maintain the signal that arrives at the base station at a constant level. So the output from the handset goes up and down. So we developed this system here where we could put a mobile phone on each side of the head of these head phantoms, and then we could drive around and monitor how the output power of the phones varied with time, and we could then or maybe I should just say a little bit about that power control. So the power control characteristics of GSM and CDMA phones are quite different. In GSM, it's a relatively slow variation of the phone power, and it's controlled by two mechanisms. There's a slow associated control channel, and there's the fast associated control channel. So one changes it at only 2 times per second, and the other at about up to 50 times per second, and in 2 dB increments. So 3 dB is a factor of 2, so 2 dB is, I don't know, 0.6 or something factor. And then, so that's changing much more slowly than the IS-95, and these CDMA standards, they need to react much more rapidly to control the power, and they were reacting at 800 times per second, but it only increments the power by a small increment, but overall it gives rise to some variation in the output power. And what we wanted to do was alter the relative rotation of the two stirrers, so this variation in power could have the same low frequency envelope as we measured in the real environment using this setup. So for IS-95, this is the low frequency power envelope going from 0.1 Hertz up to 10 Hertz. You can see that we have quite a wide spectral envelope here, going up to higher than 10 Hertz. And by tuning the speed of the stirrers in the chamber, we could mimic some characteristics of the spectral envelope. Not every characteristic, but get it reasonably close. So we ended up with similar sort of peaks and troughs in the characteristic here in the chamber due to the stirrer modulation that we got in due to the power control modulation of the envelope. And similar sort of thing for GSM. This is from the measurement, and this is from the chamber, and we have some components looking relatively similar. Obviously it doesn't have all the characteristics, but we've given some physical reality to that variation that wouldn't have been there. And we found that for CDMA, a ratio of 4 to 5 for the speeds of the stirrers was appropriate, and for GSM 1 to 2. So there was questions about the stirrers earlier and what happened in terms of the stirrers in the sham chambers. Well, this is what we ended up with. Rats at 900 megahertz. The stirrers rotated at 8 and 10 rotations per minute. And for the mice, 4 and 5 rotations per minute. The reason that it's different between 900 megahertz and 1900 megahertz is due to the wavelength. The wavelength is half the size at 1900 megahertz approximately, so the mode density is much higher. So to get the same variation in mode, the stirrer only needed to rotate at half the speed. And for GSM, I already said that the power control is much slower, so the stirrers are rotating more slowly as well. And we had 2 and 4 RPM for the rats and 1 and 2 RPM for the mice. Now, So we have different stir speeds for different modulations, but we have a common control group. How do we deal with that? Well, the simple thing is that if we look at over an hour of exposure, we already said we're using the amplifiers for GSM in one 10-minute slot, and then we're using the same amplifiers for CDMA in the next 10-minute slot. So during the first 10 minutes, we're exposing at GSM, and all the stirrers in every chamber, whether it's GSM, sham, CDMA, rotate at either 2 and 4 or 1 and 2, depending on whether it's a rat or a mouse chamber. And then when we switch the modulation, the stirrers change their rotation speeds in all chambers again to 8, 10 or 4 and 5. So if there are effects due to the rotation of the stirrers, it's the same in the sham chambers and the exposure chambers. And that repeats over the full exposure period until it stops. And during the periods where the animal care workers are going to go in and perform their duties, the stirrers were stationary. So what we did monitor was we monitored the current to the stirrers. So if the stirrers were starting to see higher currents, increase in currents, then we could determine that the maintenance staff needed to go in and lubricate the stirrers, and this way we could maintain the noise levels due to the stirrer rotation at low levels, and there wasn't too much noise from the stirrers present in the chambers. A little bit of mechanical noise, there was a gearbox, a little bit of gearbox noise, that was all. Now, noise is important in these studies. Basically, we don't really want it, but it's present because of the air conditioning and because of other factors, a little bit of mechanical noise due to the stirrers. So, we introduced into the environmental monitoring system noise measurements, and the noise was measured in all the chambers. But at the beginning of the project, it was discovered that depending on exactly where the chambers were located in the facility and their proximity in particular to the air outlet fan, then the noise levels changed. So you could see for the female rats, which are on the opposite side of the facility from the outlet fan, the noise level was a bit variable, but between 50 and maybe 57 dBA. But for the male rats, we had bigger variation. For the quieter chambers at about 50 dBA, going up to about 62 dBA. Now, we didn't want the noise to be a factor affecting the study, so we introduced white noise, which was similar to the noise generated by the air conditioning system, into all chambers to equalize the noise level in all the chambers to this level of about 62 dB. So when you get an idea of what that means in terms of what happens in a typical environment, so that's equivalent to a typical air conditioner or conversational speech. So it's not excessively loud, but it's not quiet like a whisper. So just to illustrate what I meant, so we had air inlets coming up this side. There was a huge whatever it's called, the word has gone. Anyways, this conduit where the airflow is coming up the side, and air was then fed into individual chambers from this side, and what happened was this air was at a lower temperature than that required, and each individual chamber had its own steam reheating coil where it could control the individual air temperatures going into the individual chambers so that the exit air temperature from each chamber was maintained at a constant level. The female rats over here, they had a lower noise level, and the male rats had a somewhat higher noise level. This outlet fan being the thing that was causing the most noise problem. In addition to adding white noise to the chambers, what we discovered was that when we had high field strengths inside the GSM chambers, because the RF was pulsing on and off, we ended up with a field-dependent buzzing sound, where the fundamental frequency was the frame rate of the GSM at 213 Hertz, and we recorded that, and this was the spectral content of this signal. So it was going up to around 13, 14 kilohertz in its component, and we recorded that, put it on an MP3 player, and we mixed it with the white noise and introduced it into all the chambers at the same level as in the highest GSM chambers, so it would mask that, and that was on all the time, whether it was CDMA or GSM on-off cycles. Drinking water. So there's more than 3,000 rodents in the study who had to supply drinking water. So typically that is either done using water bottles, but when you've got 3,000 rodents, that's an awful lot of water bottles to change. So they wanted to use an automatic watering system where you have licksits that the animals can access and allow the flow of water. Now, if we'd used water bottles, the water absorbs RF energy, and we would have ended up with drinking water that had a dose-dependent temperature rise, and that could have been a confounder in any experiment. So we would have had to shield all those water bottles, use metallic water bottles with metallic sippers, and that could potentially have caused overexposure of the animals. Likewise, if we'd used a standard drinking water system with licksits, the licksit valve has a very thin, it comes down to a relatively small diameter here, 5 millimeters, with the licksit valve stem here, stainless steel again, 1.5 millimeters. If you put any small metallic structures inside an electromagnetic field, then the field intensity around that structure is enhanced, and the field around these licksits would have been enhanced, and the SAR in the mouth of the animal and the tongue would have been increased many times above the desired exposure level, where potentially we could have seen RF burns in the mouth parts of the animals, and that could have deterred the animals from drinking, and again we would have had a huge confounder in the experiment. So important was how to go about designing that so that we could safely supply automatically water to the animals in metallic tubes so they didn't absorb RF energy. And why won't it go forward anymore? It's a very good question. It will go forward, but it's gone forward too far. Right. So what we developed was effectively a shielding and choking tube to prevent RF currents from flowing from the water system into the mouth parts of the animals, where it was specific for the individual study. So it's frequency specific, and it's related to the wavelength. So we had the licksit here. We found if we just use a standard tube for choking currents, that didn't really help, and we had to increase the diameter of the tube and extend it beyond the front edge of the licksit, so it was effectively shielding the licksit, and that way we didn't end up with fields around the sipper here, but we ended up with fields around the periphery here. And to ameliorate that effect, we then put a disc on the end that increased the periphery, spreading the field around a much larger circumference, reducing the overall field strength. And we then inserted a plastic insert into the tube here, so that there was no way that the animal could touch this outer part of the... I'm not sure how I did that or how to undo it. Yeah. Oh well, we'll worry about that in a minute. In the cage here, we had a grommet. Oh, I've got a nice little hand shape now. And that grommet was ceramic rather than metallic. We needed a grommet to stop the animals from eating their way out of the cage, but it couldn't be metallic because that would again have affected the fields around the structure. And the grommet then aligned with the lixit, so the animal could only access where they needed to get to. Okay, I'm back to normal size. So we fed each pair of cages from a centre water tube which meandered down the centre of the rack, and then the cages were introduced from each side. The grommet gave access to the water system. Yeah. And I think that's pretty much covered it. Here you can see the cage rack, and these are the fiberglass materials that we used to form the rack. We had these polycarbonate cages and polycarbonate cage lids where there were slots milled into the lids to give the airflow into the cages. Right, so we then introduced sensors into each chamber. We had a noise sensor with a microphone and a tube to bring the noise out of the chamber into the sensor box, temperature and humidity sensor, airflow sensor, and there was also an oxygen sensor present. This was connected to door switches, so if a door was opened, the RF would be switched off to keep the staff safe. Warning lights to indicate the status of the system, red for when it was on, green for when it was safe to go in, and blue to tell you need to close the door because the exposure was going to start shortly. And a light sensor and an RF sensor. And then we had a big cable loom to all the instrumentation, the E&H fields, all the stirrer motors, etc. And this is what a typical equipment rack looked like, with signal generators, data acquisition for the environmental sensors, measurement servers for the field sensors, and power supplies, and rack of amplifiers. The amplifiers were water cooled to keep them quiet, so we didn't introduce noise into the facility. So in terms of what we acquired, we sampled the fields at 1250 times per second, and then we averaged it over 1 second periods and sent every 20 seconds that information to the computer, and it was stored to the log file. And the SAR was calculated and reported every 20 seconds. But the SAR was only calculated during the exposure periods. We didn't calculate it when there was no exposure. The environmental parameters were measured every 20 seconds and again stored into the log file. So we would end up with 4,319 values per day for each measured parameter, and 1,798 values relating to the exposure. And that was then summarized in these tables on a daily basis. So this was for exposure. You can see the target SARs, the actual SAR that was achieved on that day with the standard deviation and the minimum and maximums, and how many were in range and how many out of range. And that was done for all the parameters that were measured. And again, you can see here the off periods in the morning for the animal husbandry, It was then, the system was on for a while, and you can see the field strengths here for the high, medium and low chambers, the off period in the afternoon, and then the exposure overnight. The exposure facility here, we'll talk more about the dose groups later, but the maximum number of animals that could be housed in the chambers was from 111 to 216, depending on whether it was rats or mice. The power was switched on a slot-by-slot basis for GSM into the different chambers, and that's illustrated here, where the number of amplifiers allocated could maintain the required SAR levels. And similarly for the CDMA chambers, where individual amplifiers were allocated for the whole 10-minute period because there was no on-off slots. So that's basically what I want to say about the chambers, and then I'm just going to run through a few photographs in the last few minutes just to show you a little bit about how they were made and how they were shipped and then installed in the facility in Chicago. The chambers were made by a company called Vetter in Switzerland at the same time as they were making all the metal work for the new football stadium in Zurich. So these were relatively small compared to the things that they were making simultaneously. And then they were stored in this huge building here, which used to be for an iron foundry in Switzerland and was fallen out of use. Now it's the business park, but at that point in time it was empty. And you can see pictures of the external views, the internal views, and it was in this facility where we installed all the stirrers, the lights, the guard for the stirrers, the cage rack guides. All the internal fitting was done in this room. This is one of the sensor boxes being fit, and you can see the chambers here, and this was the full team of people that were involved in Zurich in making these chambers. We then were testing the jigs that we'd made for moving them once it got into Chicago on the crane here. And there you can see a good number of the chambers, so all 21 chambers were present there. And from there, they were wrapped in plastic to waterproof them, put into wooden crates. From the wooden crates, they went onto lorries, and they went from Zurich to Basel, where they were put into barges, and they were sailed down the Rhine into Rotterdam, where they were then put onto ships. Ships, they came across the Atlantic, through the Great Lakes, down to Gary, which is just south of Chicago. And then we arrived, and we marked out where all the chambers needed to go in the facility. And then the next day, they would arrive a few at a time by truck from Gary, where they were decrated. And the crane that we hired arrived. Here's the Chicago team, including me. They then lifted out part of the so part of the facility was under the building at Itri, and part was out under the sidewalk. The part under the sidewalk, we removed the concrete slab to open up this hole big enough for the chambers to go in. They were then lifted down through the concrete slab into the facility, and then we attached these wheels onto each chamber and then pushed them through the facility, literally, to their designated locations. And when they were all lined up in the right places, we then left the facility, and at that point they then attached all the ductwork for the air conditioning, put in the flooring, and then we came back later and put in all the electrical system, And ultimately, it looked like this. This is half of the facility. Chambers facing this direction. Then there was another set of chambers behind them. And in summary, I've shown you some nice photographs. I've talked about the communication standards and signals and how they relate to current standards and how they were chosen with these different low frequency power envelopes. I've talked about the reverberation chamber, electromagnetic environment, how it's homogeneous and isotropic, the characteristics of these chambers, and talked about the watering system and how we monitor the environment and how that was put into log files, so it provided a daily record of both the environmental and exposure. And yeah, so thank you for your attention.
Thanks. For panel 2 members, there will be a quiz at the end of the day. So we have some time now before we take a break for questions for Dr. Kepstick from the panel.
Yeah, Larry Whiteley at Pfizer. So a couple questions. So were animals rotated in the caging up and down, side to side?
Okay, yeah. So what I haven't talked about too much just now, because I'm going to talk about it more in my next talk, is the dosimetry. So obviously there is a bit of inhomogeneity there. But as the animals move around their cages, it evens this out. But also the cages rotated on a twice weekly basis, I want to say. Maybe it was weekly basis, around the cage racks, so that at least on average over the whole study, they definitely got the same exposure.
So you also made a comment about the 10 minutes on, 10 minutes off, and modulating between the two different exposures. Was that done for a biologic reason, or was that done because you didn't want to make two separate systems for the different exposures?
So there was some previous studies that showed that the intermittency of the exposure was an important factor biologically. I'm maybe not the best person to answer that. Maybe Niels can say something, because he knows the history better than me.
Because I'm older. So at the time prior to the study, there were studies running by Motorola in the Urs Eddy's lab, in which he has chosen the scheme based on previous in vitro work. This idea was taken over for the Perform A, and the European project had also an in vitro program called Reflex, and there this scheme was used and showed effect depending on, showed biological effect when it was intermittent and no effect when it was not, was continuous. And that's why this selection was made. It is based on something, but still kind of arbitrary.
So I don't think we need to answer this now, but at some point there was a European study that was just published just a few weeks ago where they used continuous exposure to rats. So I'm interested in how with lower frequency, so how did the exposure between what was done here with that study, because they saw a similar tumor response in that rat study. So I'm interested in how this study and that study compared from an exposure point of view.
James Lin, and before I ask my question, actually I'd like to again ask the alternation between the GSM and the CDMA. I think Dr. White had sort of allayed my concern by saying that these were done in separate chambers. But for some reason, both of you have used the term alternate between GSM and CDMA. That's why I asked the question. Were you alternating between on and offs? Or is that just a slip of the tongue? Were you indeed using CDMA in one chamber, GSM in another chamber, even though in both cases you had the 10 minutes on, 10 minutes off? I have another question after that.
Yeah. So in terms of exposure groups, there was 7 exposure groups for each species and each sex. And those exposure groups were, and they were in separate chambers. There was the sham control, which was common to both GSM and CDMA. There was then 3 chambers for GSM exposure, high, medium and low, and 3 chambers for CDMA exposure, high, medium and low. So yes, it was alternating. It was sending the energy to the GSM chambers in 10 minutes, and then the next 10 minutes it was sending the energy to the CDMA chambers. So they were completely separate.
All right, thank you. That clarifies. So you were sending a different modulation to a different chamber at different times.
Yes.
So, okay, all right. My real question is that I think it's very interesting that you mentioned something that reading the report did not really reveal, that you use the different lighting systems. In your case, because of your concerns about RF exciting the fluorescent bulb, therefore you chose to use incandescent. I believe most of the historical data were obtained based on lighting using fluorescent lighting. So that potentially brings up a very interesting observation, that is, what is the difference between these 2 types of lightings? I know geometrically you used 4 corners of the room rather than the top of the room. That's one difference. But the heat and the color temperatures are both very different for those. So how, in this case, then, can you compare any of the historical data, well, these mice and rats, with what this project had used? They were entirely, at this moment, it seems to me, they were entirely under different lighting conditions.
I mean, obviously they had the diurnal cycle.
So it has nothing to do with the diurnal cycle.
I know. I'm just saying that was something that they had. But I agree, and this is why we're mentioning it here, that the colour temperature of the incandescent lighting is obviously very different to the colour temperature of the fluorescent lighting that's normally used.
Very unfortunately, that introduced a huge uncertainty in terms of how one might use the historical data that you try to rely on with the study data.
So, I mean, this is, I think, not my part as an engineer to attempt to answer that.
Dr. Booker?
Yes, you've hit on something that's been a very perplexing part of trying to understand the results of this study and how to try to bring some perspective of the historical background of these animals into interpreting these tumor data. But I think that lighting is one thing. Many of these studies were done at other laboratories. There's a slight variation in food content composition. There are a variety of different housing conditions. There are different methods of exposing these animals, either food, drinking water, or gavage in some cases. So all of these things are going to have to be really thrown to the panel too tomorrow and the next day to try to sort through how much you want to rely on historical data from other types of studies, but using the same species and strains in interpreting these studies. So it's not an easy question to answer.
Dr. Harkema.
So maybe you answered this already. Larry asked about rotation of the animals. I understand that. But I assume the phantoms were motionless and they weren't robots. And so I was just wondering if you could talk about activity. Does activity of the animals have, in terms of efficiency, energy efficiency, does that have should we just discount that or what?
So the topic of my next talk
You can pay me later
is the
for
dosimetry.
asking
So
that question.
I hope that I will answer most of that
Okay.
in the next talk.
Yeah, and just a comment about the lighting. So I'm surrounded by plant biologists at Michigan State, and lighting and studies are ongoing on incandescent and fluorescent all the time, and you can learn a lot from how the plants behave, and maybe you can translate that to the animal. I don't know.
Dr. Felton?
This might also be a question that you'll talk in dosimetry, but maybe not. So I wanted to make sure I understood the basis for choosing the 900 megahertz for the rats and 1900 for the mice. And you said was not so much because of the biology, but because of the coupling in terms of the relationship of the external field to the internal SAR, and what does that mean for trying to understand this for a species that's of a very different size?
Okay. Can we defer that question till after the next talk if it's still appropriate? I hope I answer that.
Dr. Karate?
So you had data about the weight of mice versus rats, and then female versus male, and these are like average data. So I was wondering, if we just look at like male rats only, what's the statistical variation from one rat to the other?
That's
and same
also
goes for
in the next
different groups.
talk.
Okay, thank you.
Other questions? Yes.
I think this is this talk. Could you just elaborate a little bit more on the ambient noise in the rat's hearing range, say 30 to 90 kilohertz?
So at the time, at the beginning of the study, we were asked to measure the noise using dBA. Now, dBA is tailored towards the frequency response of human ears. I appreciate that this is the case. Now, certainly this GSM noise that was introduced, we measured that, and certainly there was nothing above 14 kilohertz for that. So I can say that, in terms of that part of the noise component, there wasn't anything up to 90 kilohertz. Now, in terms of what was coming from the air conditioning system, it's not something that we specifically measured or were able to measure, was the high frequency content. And as I say, we tried to keep the stirrers well lubricated, so we didn't introduce any high frequency squeals or anything like that from the mechanical movement of the stirrers. So we hopefully kept on top of that, but I'm not able to give you a complete and comprehensive answer to your question.
One last question, and then we're going to take a break. Dr. Lang.
In a way, so following up this question is bringing up the GSM modulation, the 213 or 217 hertz that got introduced as a noise. Perhaps it's more of a logistic problem. How was that not prepared for? How did that noise get transmitted into the chamber itself?
It was generated inside the chamber due to the high field strengths.
Say that again?
It was generated inside the chamber.
It's not from the transmitting system?
No.
How did it get generated in the chamber itself?
If we fully understood that, it would be fantastic. But we know it's a very bright noise, so it's not a thermally related phenomenon, because that would give a dull noise not with high frequency components. So
well, it has to be an electrical noise from the transmitting system, because inside the chamber you have animal cages and the stirrers and so forth. Yep. How would the GSM modulation, which comes from the electronics, be somehow transformed into a mechanical noise inside the chamber?
So it seemed it was related to stirrer position. So, exactly quite what the mechanism was. We're not sure. We did all sorts of things to try and stop it. We put on damping materials onto metallic surfaces, all sorts. Everything we tried didn't remove the noise that we generated.
Conceivably, it could be because it is associated with the switching. Therefore, some mechanical device associated with the electronic power transmission system got that noise transmitted into the chamber rather than what you're suggesting inside the chamber. An electronic signal gets converted into a mechanical signal. So that's kind of perplexing.
So, I mean, we did have switching on a slot-by-slot basis, but this switching was all electronic with pin diodes, so there was no mechanical noise associated with that switching.
You're doing high power though?
No, it was switched in the off periods, so we only used 4 of the 8 slots, and we were on one slot, and then we had a guard slot, and then on the next slot a guard slot, and we switched during the guard slot when there was no energy present.
Yeah, there's a lot of metal, and there's welded metal, and there are non-linearities there which I think were the cause of the vibration generated. It was a demodulation by the non-linearity of the conductors in there.
Dr. Wolf? Okay, so we will take a 25-minute break and resume promptly at 11:30. We'll have then another presentation by Dr. Capstick and have a little bit of a late lunch today. Okay. Get started again, Dr. Capstick. You have the floor yet again.
Okay, so the continuing story where we've learned about the fields that will be incident on the animals, and now we're going to move on to look at how those fields interact with the animals and how that relates to the specific absorption rate. So here is my talk about the dosimetry for this study. I'm going to do some broad introductions and talk about the dosimetry and numerical dosimetry specifically, and the anatomical models of the animals that we used. I'll reiterate the exposure environment and how that then folds into the modelling we did. Look at the whole body and organ specific SAR for the animals, and how we then validated that experimentally. We talked about the water system before. Well, we'll show how we validated the fact that that didn't overexpose the animals, and talk about the uncertainty and the variation in the exposure, and then wrap it up with some summary and conclusions. So we'll start from basics. What is dosimetry? So dosimetry in this field of health physics and radiation protection is the measurement, calculation and assessment of the internal exposure to the body. So for non-ionizing radiation, which we're talking about here, and specifically non-ionizing radiation in the radiofrequency range, the exposure quantity is the specific absorption rate. Specific absorption rate is expressed in watts per kilogram. So it's the amount of energy absorbed by the body and divided by the mass of the tissue that it's absorbed in, where that mass could be a localized mass or it could be averaged over the whole of the body. So for humans, there's 2 regulatory limits. There's the local peak absorption, which is depending on which region of the world you're in, either averaged over 1 gram of tissue, which is approximately a centimeter cube, or 10 grams of tissue, which is about 2.2 centimeter cube, depending on the density of the tissue. And then the other limit is for the whole body SAR. So when we talk about exposure from a mobile phone, that mobile phone is a small device. We typically hold it close to the body. Then it's the peak local SAR that becomes the exposure limit and not the whole body average. Whereas, say we were working close to a radar or something like that, then it's probably the whole body average that becomes the limiting factor. And we'll look at how that then can be translated into the peak and whole body absorption in the animals in the study. It's important to realise it's not possible to measure the SAR directly in the subject, humans or animals, but what we do is we measure the fields that are incident on the animal or the subject, and then we perform some numerical dosimetry where we model an anatomical model of the animal and the exposure fields and assess what the internal fields are inside that anatomical model, and then we validate it in a simplified model of a homogeneous phantom. So what determines SAR? Well, there's aspects that relate to the subject and there's aspects that relate to the field that is exposing that subject. So in terms of the subject, the size, the weight, the electrical properties of the tissues, the anatomy. So where you have anatomy is inhomogeneous tissues. You go through different tissue layers, different organs, and how they're arranged inside the body varies how the fields are absorbed by the body. And the posture can also vary the SAR. In terms of the field, there's the strength of the field is obviously very important. The proximity of the source, so how it interacts with the body depends on how close it is. And we have so-called reactive near field. So when you have a phone next to the head or in your pocket next to the body, then that's typically a reactive near field environment versus the far field. Now, that's just the coupling mechanism. When we do the dosimetry, we determine the fields that are induced in the body, and it doesn't really matter what that coupling mechanism is. The dosimetry tells us what the SAR is in the different tissues. The frequency of the EM field is also very important. If you have a long wavelength and a small subject, then it's very difficult to get interaction between the field and the subject. Whereas if you have an animal that's of a similar size to the half wavelength in free space, then the interaction tends to be somewhat more enhanced over other situations. The direction of the field. If you take myself as a subject, if the field is polarized vertically with respect to me, as opposed to horizontally, then depending on the frequency, you would get different interactions that would occur. So the direction, the polarization of the field are also very important in determining the amount of energy that will be absorbed in the subject. This is a graph we've seen already. So knowing that size, weight are very important, then and also the frequency, etc. We can see that the mice and the rats are obviously very different sizes. You've probably observed this. The male and female rats are also different sizes. Then, exactly how we might expose them could be a function of those factors. Numerical dosimetry is where we take an anatomical model of the subject that we're interested in. Here it might be a rat or a mouse for the NTP studies, where all the anatomical structures or tissues have been segmented, so we know exactly this is skin, this is heart, this is muscle. We can then apply to those the appropriate properties. And here we just have a couple of examples. So it talks about slice distance here. So these models were made up from cryosectioned animals, where they were then photographed, and then the individual tissues were determined from those cryosections, and then it was built up into a 3D computer model. And for the mouse, the slice distances were somewhat smaller, and we had various different models available to us. So once we know those, where the tissues are geometrically, we can apply to them the appropriate electrical parameters. So when I talk about electrical parameters, what we're interested in here is the relative permittivity with respect to that of free space, and the electrical conductivity, how lossy the material is. And this is just an example for 900 megahertz that we took from tissue database, and we assign the appropriate properties to the appropriate tissues, and that all goes into the computer model. And then we can apply mathematically fields or travelling waves to those anatomical models and end up with maps of how the energy is absorbed in the animals. So we asked the question of why did we expose mice at 1900 megahertz and rats at 900 megahertz? Here we see the reason why. So here we see the mouse, and this is a plot of the surface SAR, so looking at the surface of the skin, and we can see we've got high absorption in the tail here and high absorption in the ears if we were to expose it at 900 megahertz, and we've got a more homogeneous distribution of SARs, not homogeneous but more homogeneous distribution of SARs at 1900 megahertz, whereas at 900 megahertz we have a distribution like this for the rat, and at 1900 megahertz like this we have again maybe a higher exposure of the tail than the body. But I think more instructive is if we take a slice down the center of the animals, and here we see a medium-sized mouse at 900 megahertz. We don't have such high absorption in the rest of the tissues of the animal, but high absorption in the tail, and we get a much more homogeneous distribution of absorption at 1900 megahertz. It may be there's other frequencies where we would get a more homogeneous distribution, but one of the fundamental requirements was that it should be communications bands associated with mobile devices, and that meant we were in the 800, 900 megahertz region, or 1800 to 2000 megahertz region. Whereas for the rat model, at 900 megahertz, we got a good distribution of SARs throughout the animal, and a rather less homogeneous distribution at 1900 megahertz.
What was the orientation of your electric field for this model?
It was impinging from all directions. Yeah. So at that point, when we saw these SAR distributions, it was determined that we should expose the mice at 1900 megahertz, the rats at 900 megahertz, because that way we exposed a wider variety of tissues. In the NTP study, we weren't trying to mimic a phone held next to the head. We were trying to expose as many tissues as possible because we don't know where the potential sites of interaction of the electromagnetic fields with the body would be. And I mean, it's kind of fortuitous that that was the case, because now probably using the mobile phone against the head and just exposing the brain is not what's happening. People are using their phones in many other different ways, and all putting it in different pockets. They used more for data than voice calls now. So to summarize, we were then, after determining that, we set up the exposures to be at these two frequencies, 900 megahertz and 1900 megahertz, for rats and mice respectively. And then we performed the numerical dosimetry, the detailed numerical dosimetry, based on those frequencies. And that numerical dosimetry gives us two outcomes. The whole body SAR, where we take the total energy absorbed in the animal and divide it by the weight of the animal, and the organo-specific and tissue-specific SARs, where it's the energy absorbed in specific tissues divided by the weight of that tissue. So here we have a range of 0 to minus 20. So 0 is the peak SAR to minus 20 decibels. So that's a 100-fold change in energy absorption from the bright pieces to the dark colours here. So we had anatomical models that we used for the dosimetry, again all derived from these cryogenically sliced animals at different animal weights. We had from small pup rats up to male rats and intermediate sizes as well, and a range of mouse models available. So that's one part of the equation. The other part of the equation is the electromagnetic environment that the animals would be exposed to inside the reverberation chamber. So the reverberation chamber looks like this. It's this resonant box. We have these mode stirrers, and they're scattering the energy inside the chamber. And there's different potential ways that you can represent this exposure environment. But what's happening is the energy is scattered, it's bouncing off the metal walls of this chamber, and it's impinging upon the animal from all different directions. So if you integrate over a sphere around any animal, then the energy coming in from every direction will be approximately equal. And this is what's known as an isotropic field. What's more, the polarization of these fields will be random, where on average every possible polarization angle has the same probability. So we can have random waves arriving from different angles, or other sets of random waves arriving from different angles. But what we can do, we can always sum them all up and boil them down to just 12 plane waves, impinging on the sides of a cube with two orthogonal polarizations. And these are the two methods we use. We can use random plane wave method, where we need hundreds of random plane waves over hundreds of replications, so it's computationally intensive, or we can just use this 12 plane wave method as a reasonable proxy for what happens. So just to try and illustrate that, each of these dots is a random plane wave. They've got random amplitudes, which the amplitude is the distance from the center. The further from the center, the higher the amplitude, and then random phases given by the phase angle. So the angle here is the phase angle. And we generate sets of random plane waves, and you can see a selection of 12 here. Typically we would generate sets of 500 random plane waves and do greater than 300 replications of this. We would then apply to them random angles of arrival, random polarizations, and then apply them to this anatomical model of the animal inside this numerical dosimetry tool. And what we find out is, there's some variation to start with, but then if you do sufficient replications, it settles down to a constant level, average. And that's how we went around modeling the environment. Once we've done that, there's different ways we can then average over these sets of random plane waves. We can do it on a simulation by simulation basis, which is basically what happens here, or we can average the SAR over all the different sets of random plane waves. The sets of random plane waves are equivalent to different stirrer rotational angles, and then average the field over all of those, and then determine the normalized SAR. Both end up giving the same answer effectively by the end. But as I say, we do need to have a large number of random plane waves and a large number of replications for it to end up at a consistent value. So we then use the anatomical models that we had. We only had a certain number of anatomical models, but we want to know what the SAR is over the whole lifespan of the animal. So in between, we need to scale the animals up and down a little bit to fill in the gaps between the animals that we had available as numerical models. And we could come up with what is known as the SAR sensitivity. So this is for mice at 1900 megahertz. The blue diamonds are using this simplified 12 plane wave model, and the squares are using the much more computationally expensive random plane wave model, and they give very similar results. And the differences here we can take into account in the uncertainty budget. And likewise, so basically the higher the value here, the more sensitive it is, or the easier it is to induce specific absorption rate in that animal. So when they're smaller, we require lower field strengths to attain the same SAR, and we adjust the field strength that we expose the animal to over the period of the study based on the average animal weight in a particular chamber. So as the animals grow, we have to increase the field strength to maintain the same SAR. And for the rats, when they're very small, the pups down in this region, they're less sensitive and they come up to a peak when they're at approximately half a wavelength long, and then the SAR sensitivity reduces again. But again, we maintain the field strength such that the SAR remains the same, irrespective of the SAR sensitivity. Also, when we put them on the same graph here, the mass and the mouse mass, we can see that the SAR sensitivity of the mice is higher than that of the rats. This doesn't mean they're exposed to higher SAR. We just adjust the field strength so we achieve the SAR of the exposure group to be what we desire. So, one outcome of that dosimetry are these whole body SARs or SAR sensitivities from which we can determine what incident field we require. The other aspect is the organ-specific or tissue-specific SARs. And here we can see for rats exposed at 900 megahertz and mice at 1900 megahertz. Do this. Tissues that have got a high water content, like the blood in the blood vessels, the small intestine, the lungs, they tend to have a higher SAR, and the heart as well, a higher SAR than the whole body average. Whereas those with low water content, such as bones, and fat tend to have a lower SAR compared to the whole body average. So you can see that they're not uniformly exposed, all the tissues, and it doesn't mean that the internal fields are necessarily that dramatically different. It's related to the internal field and the conductivity and electrical properties of the tissues is the SAR. So once you know the SAR, and if you know the properties of the tissue, you can determine what that relates to in terms of the fields induced in the individual tissues. We can also see that when we look at the standard deviation across those tissues, we don't have homogeneous exposure across the tissues, and we have a range of different distributions for both k=1 and k=2. And you see a similar sort of trend in the mice as well, where the tissue is not homogeneously exposed. There's variation across each tissue, and variation between the individual tissues, either above and below the whole body average. So, specific interest to the outcomes of this study is what happened in the brain and in the heart. And what I've done here is just draw those out to present them. It's fair to say that the heart and the brain average SARs vary from the whole body average, and the ratio between the heart and the brain and whole body SAR changes with age and sex. The only reason it changes with sex is that the animals tend to be different sizes and slightly different shapes between the two sexes. So for mice, the heart average is higher than the whole body average by a factor of 1.72. I base this only on those anatomically correct models and not the scaled models. And there's some variation over the weight range, but it's relatively small variation, the standard deviation being 8%. And when we look at the brain, the average brain SAR, and when I say brain here, I include the midbrain and the cerebral hemispheres, which were separated as different entities inside the anatomical models. On average, it was pretty much the same, but you see the standard deviation is 27%, so it varies as the animal grows. And when we look at the rats, we have wider variation, partly because we have male and female rats and they're different weights. But always the heart is more highly exposed, but the amount that it's more highly exposed with varies quite dramatically, from being almost the same as the whole body exposure to being up to 3 times higher. And the brain average SAR, on average is similar to the whole body SAR, but again we've got more variation there than in the case of the mice. For the case of the rats, the pups were exposed with the dams, and also the pregnant female was exposed from gestational day 6, I think. So we did dosimetry relating to both those situations of the pregnant female and the pups. And what we found was that, when the pups clumped together, all sleeping on top of each other, then the SAR of the pups compared to a single pup is somewhat higher. And we saw some enhanced SAR in the tails of the pups, which was considered as possibly of concern, but they're relatively small in terms of weight, so tend to shed heat much more easily than a larger animal. The dam has its exposure moderately enhanced when it's in close proximity to the pups, and the pups on their own have similar exposure to the dam for the same field conditions. So if we just look at how that relates to the SAR sensitivity that we saw before, Over here we have the weight range of the pups up to the point where they're weaned, and here we have the weight range of the dams, and we see they overlap with each other. So what happened in reality, the dams were weighed and the exposure field was set based on the exposure of the dam. So the pups, initially set off underexposed and migrate to being marginally more exposed than the dams. But on average, the exposure was very similar to that of the dams. So, what I said at the beginning was that human exposure is controlled based on two elements: the peak spatial SAR and the whole body SAR, and whichever is higher then becomes the limit in force in the various standards. So if we take for rats the three models we have here, we can look at the whole body average SAR sensitivity. So this is the SAR per volt per meter, and we can see, as we saw on the graph before, as the animal grows, the SAR sensitivity decreases, which means our exposure field has to increase to maintain the same SAR. Here's the whole body standard deviation in terms of microwatts per kilogram per volt per meter, and so we can see that the standard deviation is high compared to the mean, which means that, as we saw in the field patterns in the animals, they're not homogeneously exposed. Now, we also calculated the peak spatial SARs. So in terms of rats, if we take a 70 kilogram human and a 350 gram rat, the standards would average over a 1 gram or 10 gram average. Well, if you scale that down from the size of a human to the size of a rat, then we average over 5 milligrams or 50 milligrams. And we can see that these peak spatial SARs, just as they would be in a human, are higher than the average SARs, up to a factor of approximately 10 in the case of a medium-sized rat, and somewhat lower for the 50 milligram average SARs. But those peak SARs, they're always higher than the whole body average SAR. And when we look at the mice, again, the SAR sensitivity decreases with mass. We have high standard deviation across every voxel. So when we do the computation, we split the animals into little cubes called voxels, and we can look at all of those voxels, and we can see we have a wide variation across all the tissues. And again, for the peak spatial SARs, now the mouse is about 1/10 of the size of a rat. So these have now reduced by a factor of 10 to 0.5 milligram cube or 5 milligram cube. And again, here we have a factor of 7 or 8 above the whole body SAR for the peak spatial SAR over this smaller cube, and it's a smaller ratio for the larger cube. So we do this numerical dosimetry. All happens in computers. How does that equate to reality? That's something that we need to know. And we can't measure directly in the animals or anything that's got complex inhomogeneous structures. We need to validate using simplified homogeneous phantoms. So we take this simplified homogeneous phantom we put it into the same numerical modeling environment as we've used for the complex anatomical models. And then we perform the same set of simulations to determine what its whole body SAR will be. And what we do, we then perform experimental dosimetry on that phantom using thermal or temperature measurements to see if the measurement in the end, and it validates both the environment, the EM environment that we used in the model and how that is in the reality, and the computation that we've done. So what we used was, they're not intended to look particularly like mice or rats, but they have to absorb the same energy as a mouse or a rat. So we use approximately the same weight, and then we choose a tissue simulating media that gives very similar whole body absorption as a rat or mouse of the same weight. And we use little tubes for the mice, and here's the numerical model and the SAR pattern inside the phantom. You don't have any of the complexity that you have in a full anatomical model, but that's not the purpose. And this was for the male rat. It was a full bottle, 550 grams of tissue simulating liquid, and here's the model. And this was a bottle filled to a little over half full to represent the female rat. So what you do, you put these phantoms inside the chamber, inside cages with food and bedding. You then expose them. We measure the temperature inside the phantom, and we also measure, we put temperature probes in several phantoms and measure how the temperature increases, and then when the energy is switched off, how it decays. And from those time constants and the temperature difference, we can determine the SAR. We measure the air temperature, and then at the end, we measure the temperature of all the phantoms by taking each one, shaking it, and measuring the temperature, taking the next one, measuring the temperature. And obviously, a certain amount of time elapses between when we turn the RF off and when we can measure them. So all that time, the time constant here is thousands of seconds, so it's not a very rapid decay, but we can compensate for how much we expect it to have reduced in temperature to determine the distribution of temperatures that were achieved across all the phantoms in the chamber. Now, when we did this experimental dosimetry both in Zurich and in Chicago. In Zurich, it was the middle of summer, so we did it overnight, and we pumped cooler air from outside through the chamber to try and maintain the temperature of the chamber constant. Unfortunately, here you can see what happened to the air temperature. The air temperature increased over the duration of the experiment, and if we measure the temperature at the bottom of the rack or at the top of the animal cage rack, then we had about 2-degree difference as well. So we had not only an increasing temperature, but a temperature gradient between the bottom of the chamber and the top of the chamber. So when we went to Chicago, we thought, great, air conditioning, we can keep the temperature stable. Anyways, the three of us went from Zurich to Chicago to perform this, and discovered that week the air conditioning wasn't working. So we didn't get a set of results where we could remove this uncertainty related to this temperature gradient and the increase in temperature. We tried to remove this by subtracting the air temperature from the phantom temperature. So this was a rat experiment, and this was a mouse experiment. And given this, obviously the uncertainty was higher than we would have liked. For instance, 2 degrees here represents about half a dB of uncertainty. the 7-degree increase in air temperature here. It's difficult to know exactly what that contributes to the overall uncertainty. Possibly up to 1.4 dB. So we have male rats, female rats, and these were mixed mice, half male and half female, slightly different weights. These were the calculated SAR sensitivities that we expected. These were the average SAR sensitivities, averaged across all the dosimetry done in Zurich and in Chicago. The standard deviations that we had, and the deviation of the averages. So we can see that the rat dosimetry was, the average was pretty similar to what we expected, and we had a little bit of a decrease in the measured SAR compared to the calculated SAR here, but that was within the uncertainty limits of the measurement. So let me just go back briefly. So obviously the standard deviation gives you an indication of the distribution of SARs in the phantoms. But I think what is useful to see is the full cumulative distribution across all the phantoms. So for the male rats, that was approximately plus or minus 1.5 decibels. For the female phantoms, we had 2 phantoms up here that were sort of outliers, one at 2.4 dB higher and one around 2 dB higher, and the rest were all in a similar 1.5 dB range of spread. And then for the mice phantoms, similar sort of distribution, approximately plus or minus 1.5 dB. So some of this distribution is definitely due to the temperature gradient inside the chambers, and some related to the field homogeneity within the chambers. So the uncertainty in the measurement, there's uncertainty in the E and H field measurement. There's a bit of uncertainty related to the field control over the period that we did the dosimetry, and uncertainty related to the temperature fluctuations and the temperature probe accuracy. And the overall uncertainty is around 16%. And if you remember, the difference we had in the mouse dosimetry was 14%, so it's within one standard deviation, so we could validate the numerical dosimetry using this experimental dosimetry. But just as a point of interest, and this was done outside of this study, if the air conditioning had been working, we might have expected a similar sort of air temperature variation as we see here. This was actually done in a system we developed and installed in France, where the air conditioning was aiming to maintain the temperature at 21.5 centigrade, and we see a bit of variation. So this was what we had in Chicago, with this air temperature increasing. We then had the increase and decrease, and then we could fit curves to that to extract the time constant and temperature difference to get the SAR value. Here, at the top and the bottom of the rack, we had very similar temperatures. These were 2 of the phantoms, so we've got a little bit of temperature difference here. But the difference between the numerical and experimental dosimetry was only 0.2%. That might have been fluke, it's only one set of dosimetry, so you can't draw any firm conclusion about that. But when we look at all the phantoms that were present inside that chamber, here's what we had for the NTP dosimetry, this variation of 1.5 dB or so. Here, where the temperature control was much better, approximately 0.2 dB. So it's difficult, as I say, to know how much of this variation across the phantoms was related to the fact that we couldn't control the temperature in both of those experiments, and how much is really related to the inhomogeneity or variations in the field strength across the chamber. But the indication is it's much better. So if you remember, when we measured using this very small probe the field strengths, we saw that the homogeneity of the chamber was around 0.6, 0.7 dB, and when the cages were in there, it was a little bit higher, 0.9, 1 dB. The size of that probe, its averaging volume, is 1/8 of a cubic centimetre. The animal itself has volume and effectively integrates the field over its volume, and we're talking about 500 cubic centimetres, so it's a much larger averaging volume. And then here we had stationary phantoms. When we have animals, they're all moving around, so they'll tend to integrate any variations in field across the cage, and then the cages again were also rotated on a weekly basis, so that each animal was in a different location in the chamber. So the inhomogeneity, or I should say not perfect homogeneity of the chamber, would have been compensated by all those mechanisms. So moving on, the overall uncertainty in the exposure field is about 0.6 dB. So this is sort of -13 to +15%, that sort of region. So, you know, that's important to remember when we consider, is there a possibility that the dose groups overlapped at all? So the water system, we've talked about this, we've talked about the potential problems. We performed numerical dosimetry on this water system to design it, but we then also performed some experimental dosimetry to show that it was safe. So this was the sort of arrangement we would have with pairs of animals in cages on either side of the water system, not necessarily drinking at the same time. And we performed the dosimetry that showed with this flange choked tube sipper, then we didn't have overexposure in the mouth parts of the animal. The tube is, the choke is longer for the rats than the mice because it's related to the wavelength of the exposure field. We then made little gel phantoms for mice and rats, and we inserted into those 4 temperature probes, one in the center of the body to act as a reference for the whole body SAR, and 3 in the nose and where the mouth would be. And then we took that phantom, we placed it far away, 100 millimeters away from the watering system, 10 millimeters away, and then touching the lixit, and then looked at the rate of change of the temperature in the animal across the different points in the body at those 3 different positions. The rate of change is directly related to the SAR. So what we have here is the number of millikelvin per second, or thousandths of a centigrade per second temperature range when we're far from the lixit, when we're a bit closer, and then when we were touching. So in the center of the body we don't see much change, certainly within the experimental uncertainty, and very similar changes at all positions for the animal, possibly slightly underexposed in the short periods of time that they're drinking. So that relates to the dosimetry of the animals in a standard posture. animals don't sit there in a standard posture throughout the day. They move around, they curl up, they rear up, they drink, all these things. So we wanted to assess how that variation in posture affects the SAR, both on a whole body perspective and an organ specific perspective. As was mentioned earlier, we can measure the weight of the animals and we can set the exposure field for that average weight of animals, but they don't have all the same weight. We have some distribution around the mean weight, and that distribution means that slightly larger animals are a little bit underexposed, slightly smaller animals are a little bit overexposed compared to the average, and that gives also a variation which is on top of the basic baseline. And when it comes to the models, we had to scale the anatomical models as well, from those that were truly anatomical to the intermediate weights, and that has an effect on the overall uncertainty and variation. So in terms of postures, we made posable animal models, and then we could pose them into different postures and then apply this random plane wave. So we had an isotropic field exposure to determine how it then affects the dose to the animals. So for mice at 1900 megahertz, the posture contributes 0.2 dB. So this is a very small contribution to the uncertainty in the whole body SAR. Depending on posture, what we find is that with some postures, some organs or tissues become more highly exposed, and with other postures it's reduced, and we have a log normal distribution with a standard deviation of 1.2 dB. Now, it's not that some tissues become always more overexposed and some become always more underexposed. What we get, 0 dB, is when the animal is straight, and for every tissue, so each set of dots in a vertical line represents tissue, you get some that are postures that give an overexposure and some postures that give a reduced exposure, so slightly higher or slightly less, and they're always distributed about 0. So over the whole day of activity, we can expect that it's on average similar to that for the straight animal. So based on historical weight data, we could do an assessment of how the variation in weight has a knock-on effect to SAR variation. So this is the progression of the standard deviation of the weight about the mean for male and female rats as they grow, with the age in days along the bottom here, and the same here for the mouse weight variation. It sort of peaks and then dips and then goes back up, because if you remember the growth curves, they cross and then go a little bit further apart. And where it has the biggest impact is where the SAR sensitivity curve is changing most rapidly. So this is when the rats and mice are smaller, and that we see here, bigger variation at low age, and then actually the animals see this higher standard deviation in weight as they go up, and that reflects directly in the SAR variation. And for the mice, have this sort of response because the SAR sensitivity of mice almost becomes horizontal at older weights, so we don't see so much variation, even though the weight standard deviation increased here. As we scale the anatomical models, we introduce uncertainty, and that uncertainty contributes, in terms of the rats, maybe 0.3 dB in the whole body SAR. But a young rat anatomically is not identical to a scaled up to an old rat. So if you scaled a young rat up, then the organs grow at different rates, the body shape changes, and so there's much more uncertainty related to the organ-specific SAR. And the way we assessed this was to take anatomically correct models and scale a small model up to the large model and then compare the organ-specific SARs, and also the large model down to the small model and compare it, and also to the center weight and compare them. And from that we could gain an estimate of how the organ-specific SARs vary as we scale the anatomical models. And what we found is we end up with a log normal distribution with an offset relating to the whole body SAR difference of the individual tissues. And some are more highly exposed as they're scaled, and some become more lowly or less exposed. So to see how that relates to the overall thing, we can come up with an overall uncertainty evaluation relating to how the exposure field and the whole body SAR estimates are related, and also relate to the variation due to the elements that we talked about. So here we have that related to the E and H field measurement, the field control, which we dealt with this morning. We've then got this 12 random plane waves, and compared to the 12 plane waves, the simplified model compared to the random plane waves. We have maximum offsets, which could be up to 8 or 9%, but on average over the whole lifetime, the uncertainty introduced is down in the 2% region. We then have, relating to the numerical simulation, somehow this little box has moved from where it should be. There's the uncertainty in the dielectric parameters. There's uncertainty related to the discretization of the model. And there's also uncertainty related to the simulation method and its convergence. And they all add up to about 4% for the rats and 1% for the mice. We take all these simulations and we fit curves to them, and related to those curves that we fit to estimate what the fields should be that should be applied to specific animals of a specific weight. There's a little bit of uncertainty associated with that, which is shown there. There was uncertainty related to, for the whole body SAR, related to the scaling. And then we have this variational analysis. So the variation related to the posture averaged over the lifetime. Variation, growth rate. I didn't mention this. So when the animals are growing quickly, we measure the animal's weight. We put that in the system. We set the field, exposure field, to the correct value at that point in time. The animals then grow, and as they grow, that exposure field is no longer the correct field to get the exact SAR that we want. So when the animals were growing very rapidly, then they were weighed twice a week, and it was updated in the system. So when the animals are very small, they're growing very rapidly, we introduce at these young ages uncertainty related to that rate of growth. But After the first 50 or 60 days, this decays to almost nothing. And on average, over the lifetime, we're down at the 0.5, 0.4% uncertainty related to this weight update frequency. The standard deviation, we already talked about that, and that averages out around 4 to 6%. So overall, we have variation in the 6 to 8% range related to these different elements. So if we bring the whole body SAR uncertainty and all this together, then we can plot the SAR sensitivity with the error bars relating to the uncertainty. And here you see it for male and female rats. The uncertainty for the female rats is a little bit higher, and this is due to the fact that the slope of the curve for the mass of the female rats is still a little steeper than for the older male rats at the larger weights. And a similar curve for the mice. Higher uncertainty at young age, decreasing uncertainty as we get older. So averaged over the entire study, the SAR variation within each group, we could expect to be around this level. The lifetime SAR uncertainty is up around 20%. All these elements we've looked at before, so I won't reiterate again. If we look at the maximum instantaneous variation, then this is higher, up at around 12 to 13%. But that's only at one point in their lifespan, and it's always much lower than that the rest of the time. And over the whole lifetime, if we look at the maximum SAR uncertainty, then that can be in this 18 to 24% range. But a lot of this, don't think that this then relates to the dose groups potentially overlapping. This is uncertainty relating this transformation of external fields to internal fields. It's the overall field exposure, which was around this 13 to 15%, that is important. It's just that maybe our estimate of what the SAR might be a little bit out. So ultimately, we ended up with these exposure groups for the chronic study. We'll learn later how they came up with these particular exposure levels. The rats were exposed at 6 watts per kilogram in the high dose, and then half of that and half again, so 6, 3 and 1.5 watts, and the sham control with 7 chambers for male rats, 7 chambers for female rats, remembering that CDMA and GSM exposed animals were in separate chambers. And for the mice, somewhat higher levels, 10, 5 and 2.5 watts per kilogram, and again a common control. The males and the females exposed in the same chamber, 7 chambers again, 3 for GSM and 3 for CDMA. So when we look over the whole period of the study, and we look at the mice, these were the weight range that we had, the target SARs, the actual mean SARs that were achieved over the study period, and the standard deviations. We can see that in general we had good control, and we're very close to the target values. The worst case being here, about 3.8% lower than the target, with a little bit higher standard deviation. For the male rats, going from weaning at around 60 grams, getting on up to 600 highest case 691 grams. The target SARs, the achieved SARs, and the standard deviation. So we had good control over the entire study period and introduced relatively little in terms of uncertainty from these the control of the SAR in the chambers. And for the female rats, you see the same thing. This is not the correct weight range. I obviously failed to update that properly. Anyways, this is the correct weight range for the females. The maximum weight was around 476 grams. The SARs achieved were very close to the targets, and the standard deviations also low. So in summary, we performed numerical dosimetry, and then we validated that experimentally. We proved that this water system was safe. The uncertainties of the dosimetry and exposures were determined, and the variations introduced by the posture, the animal weight spread, and the weight update frequency was analysed. And we also looked at the full time exposure data. So the exposure groups were chosen with a factor of 2 difference in SAR levels, or 3 dB. And the uncertainty was in the exposure field was around 0.6 dB, or 14%. The exposure variation due to weight variation introduced around 0.35 dB, or 8% variation. So we could conclude that there's no overlap between the exposure groups. The uncertainty in exact whole body and organ specific SAR is higher depending on the exposure group and the available anatomical models, and can vary in this range, but that uncertainty is for all exposure groups, so they're all either a little bit high or all a little bit low, and then they're not moving together. So that's, I think, all I have to say at this point on this topic.
So we have about 15 minutes for questions, and again, at the end of the day, we will have time for discussion where we talk about all of this together. So I will open this up, but I would like to start with just a couple of questions of my own, and the first has to do with some continued confusion I have about the units of SARs. You've talked here about decibels, which I always think of in terms of noise, and then in other figures you have these microwatts per kilogram over volts per meter or something.
Volts per meter
Are those
squared.
the same? Is that what it, how do
Okay.
those two units compare?
Right. So the measure of SAR is in watts per kilogram. Now, watts per kilogram could be averaged over the whole body, or it could be looking at a cube. So in terms of humans, that's always a 1 gram or a 10 gram cube. So we scaled that to this 5 milligrams or 50 milligrams in terms of a rat, and 0.5 or 5 milligrams in terms of a mouse. And there you choose the cube that has the highest SAR anywhere in the body. And but you always express it in terms of watts per kilogram, even though it's averaged over something smaller than a kilogram. When we talk about decibels, decibels just are a ratio. They don't have units. So when I talk about, say, the brain having a SAR that is, 1.5 dB higher than the whole body SAR, that just means it's higher than the average. And when it's negative dBs, it means it's lower than the average. So it's just a logarithmic ratio and not a unit. There was a third part to your question.
No, that's good. But I have one other question.
Yeah, and then this thing about it was microwatts per kilogram per volts per meter. So this is just normalizing it to volts per meter. So this is a so-called SAR sensitivity. And the reason we calculate it that way is that when we know we want a SAR of 6 watts per kilogram, we can take 6 watts per kilogram, divide it by the SAR sensitivity and take the square root, and then we get the field that we need to expose that animal to. So it just means that I can report one value rather than a value for 6 watts per kilogram, another one for 3 watts per kilogram, another one for 1.5 watts per kilogram.
Thank you. And the second question I had is, while the focus of this study, as Dr. Bucher said in the introduction, really on hazard identification and not really risk assessment, at some point in time, these numbers will then be used for risk assessment. And I was struck by the detailed modeling that you have, including your anatomically correct phantom models, and wondering whether anybody has done that with humans to actually model both human behaviors in terms of, you hold your cell phone to your head versus you talk to the speaker versus you put it in your phone, to actually come up with dosimetry, model dosimetry in humans based on behaviors.
Yes, there's been a wide range of work done on that topic by ourselves and others, looking at exposure to the brain at different frequencies, and in particular there was a lot of interest in how children are what the difference is exposure to children due to the fact that the skull is thinner, and then also a lot of dosimetry relating now to where people put devices on their body and how that exposes different organs to different levels of SAR. A wide range of work out there.
Thank you. Other questions?
So I just want to really make sure I'm understanding the dosimeter, because and I'll ask it in a simple way. If it's expressed as watts per kilogram, and you're looking at a 30-gram mouse or 300-gram rat, say they're exposed to the same thing, is the exposure 10 times higher in an animal weighing 10 times more, or is that a fallacy because you're looking at small tissues? And related to that, is surface area a consideration in their exposure as much as body weight?
Okay, so when we talk about whole body average SAR, we look at how many watts are dissipated inside the animal. So we take that number and we divide it by the weight of the animal. So it's then expressed in watts per kilogram. Even though that mouse was only 30 grams, obviously the amount of energy absorbed in a 30-gram mouse to give you 6 watts per kilogram is much less than, well, say it's a 300-gram rat and it's 6 watts per kilogram, then it would absorb 10 times more power in terms of watts. So it's an average over the mass. Now when it comes to individual tissues, obviously individual organs have different masses, so it's the same sort of thing. You look at how many watts are absorbed in that organ and you divide it by the mass of the organ. When we come on to whether it's... So ultimately, yes, the larger the animal, for a given whole body SAR, they absorb more energy. Your question about surface area is a very useful question and very important when you come on to consider the thermal pilot study that Dr. Wyde will be talking about this afternoon, because as the animal gets larger, then its mass to surface area, get this the right way around, you've got less surface area per mass as the animal gets larger, so their ability to lose heat to the environment gets less and less. And that's why if we exposed a human to 6 watts per kilogram, yes, they'll die, no problem. Whereas a rat was okay. Niels wants to say something.
Just quickly talking about the exposure matrix. So the study was not run, and the hypothesis that total absorbed power is a relevant exposure. It was run on the assumption that locally the exposure is relevant. That can be expressed in SAR or can be expressed in E field, and SAR and the SAR and E field are very closely related, directly related, and in the exposure conditions chosen, also the H field would be related. So it was designed that all these field components are as uniformly and constant throughout animal life. So that was the concept of the exposure.
Well, James Lin, I'm glad that Niels made a remark. Actually, this is an important issue, and I want to confirm or clarify what you had said, actually, when you were talking about the difference between organ-based SAR versus a whole body-based SAR. If I use the red as an example, when you said in the heart, the difference is 2.27 times the whole body FCR. For the brain, it's 1.05 times the whole body FCR. So
that's averaged over the whole organ.
That's what you were saying? Those are the differentials between the whole body versus the organ-based?
That's correct.
So what that says is that in the brain, it is essentially the same, whether it's the brain SAR or whole body SAR. That's what you're saying, because 1.05 is essentially 1.0.
Yeah, there is some variation with age and the size of the animal, but yes, on average, it's approximately the same.
Okay, so that kind of leads to what Dr. Kuster was saying, is that the target, the intended exposure is to establish the body-wide average absorption. So aside from the brain or the heart, I can see the tail of the rodent or any other tissue of the kidney of the rodent essentially received the same average SAR. So, okay, that's a very good point to keep in mind.
Thank you.
Other questions from the panel? Oh, Dr. Mill.
Okay. It's Ron Melnick, retired NIEHS NTP. When you talk about the ratio of the peak SAR to the whole body in the heart, it was 2 to 2.5 dB higher.
So not...
Let me finish my question. That's not my question.
Yeah, okay.
But that's dB.
It was times.
2 to 2.5 dB higher.
No, it wasn't dB. It was actual ratio.
Okay, whatever.
Yeah.
But the SAR in the blood is higher, and there's lots of blood in the heart. But what we're concerned about with the heart isn't the blood, it's the tissue and the nerve sheath. So you have values for nerves, so when you're considering the nerve sheath, what would be the appropriate SAR as opposed to the peak of the heart?
So first thing was it wasn't the peak SAR in the heart, it was the averaged over the whole of the heart. And when we talked about heart, we talk about the heart muscle. So in these anatomical models where they're very small, then the number of nerves that we actually segmented are relatively small. So mainly it's the spinal cord and things like this. And, the nerve sheath on the heart is not something where we identified as a specific tissue related to that. The resolution of the model just wasn't sufficient to do that. So you would have to look really at the SAR of the heart to to get an estimate of what that might be.
Dr. Kuster?
Well, no, it's in a different place in the body, so. Yeah.
I think it would be an important information, but what we only deliver at this point is to have a good proxy of the exposure for the different body region. We do not go into sub-tissue structures. We do not have the information, and I don't think at this point it is worth to look at it, because the effort to do that would be astronomous.
Thank you. Dr. Filter, last question.
Okay, my last question is around the pups. So my understanding is that they're housed with the mother up through weaning. And what I heard you say was that when they're clumped together, you can have an increased SAR, but when they're wandering around on their own, that their exposure would be similar to that of the dam. And I'm struggling with the concept of why, for a much smaller body weight, it's not higher.
So, in the terms of the rats, the SAR sensitivity curve goes up and increases up to a weight of 100 grams, and then it comes down. And the reason it's lower at lower weights is the animal is small compared to the wavelength, and then it comes up to a peak where it's sort of I don't like to use the word resonant, but it's commensurate with the half a wavelength, and then it decreases again. So you've got the pups on this upward curve and the dams on the downward curve, so they end up at approximately the same SAR sensitivity.
In general, the animals are housed individually because this is the only way we can keep a constant, a uniform exposure. And our main concern is, when we did the analysis for the pups, is to make sure that the pups are not overexposed, even if they are clamped together. And that was then the answer of our analysis.
Okay, thank you. Very nice, very helpful. We will have a 1 hour break for lunch, 1 hour? Okay, 1 hour, and we will start promptly in an hour.